Alright. Let's get going, why don't we? We have 2 whole puzzles left. That's it. But I have some ideas after that. Let's find out what the first puzzle is. Oh, okay, good old Towers of Hanoi. There's a really simple recursive solution to this. Oh, they actually just straight up give you the solution. Okay. And they even tell you how register saving works. Just in case you didn't know that already. Okay. So basically how this works, you move the first one to here, you move the next one to here, you move the first one on top, you move the next one to there, and you just keep shuffling the stack until finally it's all over here. Yet each ring adds, each ring doubles the number of moves you need to make. Something like that. The point is, it doesn't take very many rings before it gets completely out of hand. Remember correctly, there's some kind of legend about how there's a 64 ring version of one of these that is being worked on by, I don't know, some god or something, I think it was. And if they ever complete it, the universe ends. But if you figure out how long it would actually take to complete a 64 ring version, yeah. I don't remember very much about that, but anyway. So what we want to do, if they give us the solution, we're just straight up going to use the solution. Boom. So this is a recursive. As you may have noticed, this is the move function, then we call move a few times there. Anyway. So. Let's go ahead and get this started set up. Put in our function barrier. I call this a function barrier because it just makes sure that we won't accidentally fall through the program and get into the functions below. Because due to the way functions work in assembly, or at least this assembly, the code will execute from the top down and it'll just run right into the body of the function and screw everything up. Alright, so we have damn it, how many different ways can you misspell label? And I'll put a return at the bottom. Okay. Now, this number, source, destination, and spare. So we're going to pass parameters in R0, R1, R2, and R3, I think. Unless it makes sense to pass anything in A. We could use A, I, and K. Not sure what it means by spare here. See if we can figure out how it's used. It's used as the source. Oh, it's this whatever slot we're using as our current spare holder slot. Okay. Okay. Let's experiment a little bit. Now, basically, this is the algorithm. No, wait a second. Well, something like that. That's not right, though. Because we need to have this space be the spare. Not sure why they want us to move it there. Damn it, I'd be an idiot. What am I doing? There we go. Anyway, that's not messing around. So one simple conditional check. Right at the beginning. So I think we're going to pass here. Let's specify where our parameters are first. Okay. And then we'll do we'll call their spare via slot. Now okay. So since we are using these to pass parameters, we can safely clobber them and do whatever with them. So I don't think we're actually going to need to use the stack at all. That said, let's set the stack up anyway. I can never remember what the stack set up. Okay, SDMB, SRMB. Put those right at the top of the program. SDMB, page 1. SRMB, page 2. There we go. Stack banks are set up. Now, we do CMPI. pair A 0. If 0, in other words, if the two match each other, then we will actually, let's do if not 0. Call this one shuffle. Okay. Okay, so if it is 0 though, then we do the actions to move the disc. Okay. And otherwise, we should have a return here as well. Otherwise, okay. Hello, survey. End dread. An end to the brain melting? Oh, but survey, this is where it gets worse. Because I have plans for you poor people. Because after I'm done with these last two puzzles, we are going to take this computer and we're going to make it 16-bit. At least partially 16-bit. And then I'm going to implement Forth on it. The only reason I'm going to 16-bit is because it has to be... Otherwise, this can be such a pain in the butt to handle addresses, and 8-bit is just not big enough to handle addresses properly. I would need to do some unholy mix of 8 and 16-bit if I wanted to do a proper 8-bit processor. Getting things ready for the dig site quest now. I don't remember anything about that quest. It's been far too long. I think it was pretty cool from the little bits I do remember, I should say. All right. So, we are going to need to remember... Here, let's close this. How do they... Okay, we can just output 0, 1, or 2 to directly move the magnet to where we want. That'll make things way easier because we won't have to remember where the magnet is currently or anything like that. Okay. The first 4 inputs will give you the following in order. The highest disk number, which location number to move from, where to move the pile to, and the third slot is neither the source nor the destination. Okay. So, we're going to want to load our stuff. Actually, you know what? Let's use these. Let's store these a little differently. Okay. If we do R5, R4, R3, R2, that'll leave R0, R1, and A free for to be used for whatever. Okay, let's load this stuff up first. So we want to do LDAIO, STA R2, LDAIO, STA R3, LDAIO, STA R4 and LDA IO STA R5. All right. Let's be a good little programmer and comment this. Load initial values. Boom. Okay. I'm tempted to store those values in memory, actually. What do I have for easy memory access? We could do LDMI. As long as I is kept set to 0. Here, let's do this. LDI 0. STA I. And then we're actually going to store these to memory. I'm using LDMI here because I don't have, and this is a bit of an oversight and I should fix this. I don't have a store memory immediate parameter. I could use LDI 0 and then STM. Actually, I don't need LDMI, I need STMI. Store to memory immediate. Or store to memory indirect through I mean. Here we go. Okay, so we're going to store these in memory because I just want to have them available off to the side where they won't get clobbered by anything. Hello, Colo. And then actually, let's change this back. No, let's not change it. Let's keep it the way it is for now. Okay. You know what? Before we do this, no, I'm not going to add immediate access. Okay, let me think about this. This is recursive. Where did that damn level log go? But we are going to have to store our parameters off to the side on the stack. Okay. Yeah, we do want to use A for the disk number. So let's just go ahead and do these the way I had it before. Okay. By using A, we can just reduce this code slightly to what it is right now. Then we'll do LDMI 0. Now, let's do it in reverse order, because you have to do it in some order, and we want to load 0 last, so. Okay, STA R2. LDMI. This is completely unnecessary, by the way. Actually, let's just do that right here. STA R0. STAR1, STAR2, and let me just do LDMI 0, load the first value back into A, and we are set up for the starting function call. Okay. Okay. That should be all we need to do for this part. We set up the stack banks. We load initial values. And then we do the call. And then we're into the actual function where we implement our move. So we want to go directly to the value stored in R0. So for that, we do LDA R0. A is going to get clobbered so hard. Okay. Let's do this a little differently. Let's not pass any parameters in R0. In A, I mean, that makes no sense. Actually. No, it makes perfect sense to do that. Because it doesn't matter if we clobber those or not. Because in this case, we don't need A to remain okay. And down here, we can just shuffle A off to the side somewhere. Yeah. Okay. Yeah, we'll be fine. We don't need the disk number anymore at this point because we're done. We're not going to go any deeper or anything like that. So we do LDA, R0, STAIO, and then we do LDA R1, STAIO, except we actually do, oops, LDI, what was the number that we need to send? 5 to toggle magnet on and off, okay. We'll just make that a constant. Okay. STAIO. And then if we move, toggle it again. Okay. So this should move to where we want to pick the thing up, toggle the magnet on, move to where we want to drop it, toggle the magnet off. And that's all that section should do. Now, the next section is a little bit more complicated because it calls move twice. In other words, it calls itself recursively. Which means we're going to have to do some stack saving. Have to push some registers onto the stack. Notably, we're not using any registers in here that are not already our parameters. So trying to save registers inside the function makes no sense. We have to save them outside the function. So the caller has to deal with saving the registers. Normally, the callee would deal with saving registers because that way you only have to do it once. Sometimes it makes sense to have the caller do it. In this case, because we have to, because it doesn't make sense to do it the other way. But also because sometimes you can write more efficient code. If you are not using some of those registers anyway, then you don't have to preserve them. But in our case, the caller is the person doing the register clobbering in the first place, so we need to handle saving them. If we need to save them. Which I don't entirely know if we do, actually. Yeah, we kind of do. Okay. If we get to this point, we don't need to preserve A. Except we kind of also do need to. Because we need to restore A to its previous value before we return. Yeah. Actually. Let's add a return section at the bottom. I am not a particular fan of this kind of thing, where all your return stuff happens one place. But that's because it's a behavior that is espoused by people who should know better in languages where it's not important. Hello, Bo. Woke up with a cramp? You've given up on sleep? Well, that doesn't sound fun. That doesn't sound fun at all. Okay, so we need to definitely preserve A. Sure, just preserve all the registers across this call. Like some people say, you should only ever have a single return in your entire function, no matter what language. And you should always make your flow control work out so that you always return from the same place. That only makes sense if your functions are too complicated. If your functions are so complicated you can't understand them unless they have a single return location, you have troubles. In this case, we're doing it because we have cleanup we need to do at the end of the function. But anyway. Okay. And now, we need to do the pops in reverse. Okay. Because R2 is the last on, so it has to be the first off. And then we just pop off the return stack onto PC and return. Now notably, the pushes are non-destructive, so we're not actually changing any of the values here. It's one thing that... Yep, there are no bow or U-down commands here. I have a very, very limited number of commands. You worked at the state for a week and already had a Christmas party. I guess you picked exactly the right time to start work then, huh? Unless it was really a boring Christmas party, in which case I guess you picked exactly the worst time to start. Alright. So now, A needs to contain disk number -1. I'm used to thinking of parameters as an order, but they're not in order. So we can deal with these out of order, just as long as the right values are in the right spots. So, we want the VIA slot, in other words R2, to be set to the destination. So, we do LDA. Now we need to save the value of A off to the side somewhere. So we do STA. I need a scratch pad variable. There we go. STA R3. Should do the math first. Yeah. Sub I 1. We need to set the carry first. Okay. Then we'll just go ahead and clear the carry afterwards, so it doesn't get in the way. Free food. Free food is free food. Never turn down free food. We'll do STA R3. Store it off to the side. Probably should have made the register names lowercase. Not really worth fixing now, but it annoys me slightly every time. I might still change that, but later. Okay, now that the A register is freed up, we can start moving things to where they need to go. So we do LDA. Let me think for a second here. I can't just overwrite R2. I need to free up another register, don't I? We can use K as temporary scratch space, as long as we don't expect its value to be preserved. Or we could use R4 for that matter. I think... Actually, we don't even really need to preserve R3. As long as we don't expect its value to be preserved across call. And we might want to rethink this because we might have to do something fancy with register saving in here. So these pops might need to move up, and I might just get rid of these pushes at the top and move them down in here. Anyway, we'll think about it when we get there. Because actually, I don't need to preserve registers at all in this section, because we're not doing anything to them. I mean, yeah, we're absolutely clobbering the A register. But we don't care about it, because we're not going to be calling anybody below us. It's our parents' job to make sure the A register is okay. I probably should push A at the start and pop A at the beginning. Is there anything else we're... No, these only deal with the A register. Okay. And we do pop R, PC. Yeah, because we don't need to worry about saving any of the registers here. Go away. Okay. Now, we should preserve R4. Yeah, let's just do it. Even if we don't need to, technically. Let's preserve R4. Because it's good habits to get into. Just in case this is ever called from something that uses R4, they won't clobber it. Okay. So we store the A register to R3. And then we LDA R2. And we STA R4. And then we LDA R1. STA R2. We move our destination to the spare. And then we want the spare in the destination. So we do LDA R4. STA R1. Okay, R0 is left alone for this call. And A is currently in R3, so we do LDA R3. And then we do call, move. Okay. Now, move will handle saving these registers internally. So they'll come back to us the same exact way they came in. So now we just need to do more reshuffling. So we need to do okay, R4 still holds the spare value. I think. The value that was originally in R2. So that means that R1 is currently available to be clobbered. So we do LDA R2 STA R1. R2 is now available to be clobbered. R2 is now supposed to hold the source. So we do LDA R0 STA R2. And then we do LDA R4 STA R0. Okay. That should shuffle the parameters around. And the A register is still set to what it needs to be. No, it doesn't, because we just finished clobbering it a whole bunch. So we do LDA R3. And then we do call move. Because we're missing a step in the middle here. We need to move disk from source to destination. So this exact code, which we're going to put into a separate function. We're going to change the name of this function. Piece of shit. There we go. And we do pop R, PC. Oh wait, there was already a pop R PC at the bottom. Okay. That means we need to put pop R PC up here. I accidentally removed it. Okay, who's this clobber? Nobody, because we already push and pop. Good deal. Okay, we need to change the name of this function now. Let's just call this else. No, we'll leave it alone. Call that recursive move for now. Okay. Now, we just call move in the middle here. We need to move from source to destination. Where source is stored in R0 and destination is stored in R1. Currently, that is not the way that is set up. So we need to actually do some different. This part is not correct anymore. So we need to swap spare and destination again. Although we don't have to, actually. Because, remember, spare is in R4. So we can just move this part here to there. And R0 still has source in it. So we just overwrite the spare value that is in R1 with the destination that is in R2. And that means, because we need destination to be in R1 for the next call anyway. So that'll actually cost no more extra instructions for shuffling, because we'd have to do that down here anyway. We just move it up. And then down here, we just need to set up these two values. Okay. Let's move this constant down to where it's actually used. All right. Move that little bit of documentation down. Do we even use A here at all? No, we don't need the disk number as a parameter. We do need to preserve A because we're using it. But we don't need to, it's not a parameter we're passing in. We're just saying move whatever disk is in this slot to that slot without worrying about what disk they are, because we can't tell what disk they are anyway. We just know what we've been told. Okay, let's watch this fall over. Okay, it's moving things around. Will this be a true historical moment? Known throughout the world as the very first time that I ever wrote a program that worked the first time? You can begin to see why the Towers of Hanoi can be so slow. Because you have to move the entire stack to the middle, and you have to move the entire stack to the next one, and each extra ring adds a whole, basically it doubles the number of moves. It takes a long time. All right. That wasn't too bad. Now we have the last one. Let's see if this is going to be a challenge. Okay. Landscape is 16 columns wide. Read the input 16 times to get the height of landscape at each column from left to right. Then output the total volume that landscape can carry as the answer. Okay. Oh, I see what we're trying to do. That's interesting. Okay, so it's not so simple here as looking for how much space we have below the level. We're looking for how much contained space we have. All right. That is going to be an interesting problem. Definitely not impossible. Not that complicated of a problem, but writing it all out in assembly is going to be a little bit annoying. So what we're going to want to do is start from one side of the screen and work our way over, looking for the tallest column. Every time we find a column that is higher than the previous column, we set the new highest column from that side value. I should be writing this down or I'm going to forget it. Now let me run through it mentally first. Basically, we're going to go from one side to the other. Doesn't matter which side. We'll just do it from this side for argument's sake. We'll be looking for the tallest column. So we find this column. It's currently the new tallest column. Too high. We find this one. Okay, it's 4 high. Whatever. Then we know after that, if we find a column that is shorter than the new highest column, then we add the height difference to our running total amount of water. Or our tentative running total, because we might have a giant spike on this side and then something lower on this side. We're gonna have to keep track of how many columns we've seen since the highest column and what their height differences add up to be. And we'll continue counting until we encounter another column that is the same height or higher than our current column. At which point we will commit the transaction, so to speak. Calculate the final water value for that section and add it to our running total. Then we will continue searching. We'll wipe out all of our state and we'll keep counting, looking for a new highest column, which might be the one we just found. And we'll keep doing that. We'll go from highest column to new highest column or similar sized column. And if we run off the edge without finding a new highest column, we're going to have to do a correction phase where we subtract the height difference from the columns. Oh, this might be a problem. Because I can foresee a case where we have a pretty tall column here, and then we have like medium-sized columns and a really short column. Like this example, this will be easy. But I don't know if they have any evil examples. And I'm guessing if they have 128 tests for this, they probably have lots of evil examples with edge cases and fun things like that. I wonder if there's a better way to do this. Because we can't assume, like what happens if this hill over here is low? We would have to scan ahead until we get to this point to find out. So we can't assume that just because we're at X height, we'll be able to hold back water at X height as well, because who knows what's going on over here, and vice versa. We almost need to scan the whole thing, keeping track of heights. Actually, there's a slightly dumb way we could do this that would probably be way more efficient. And that would be for each column, we keep track of the highest previous column in a value somewhere. And then we do our height difference from our highest previous column. And then we scan through the entire list looking ahead for another column that is that higher or higher. As soon as we find one, we abort, add that number to our running total, go to the next column. So what we do for here, we have no higher previous column. Our highest previous column is 0 for the map edges, basically. So we go, we are X height versus 0. Okay, we're in the new highest column. Boom. For here we go, okay, we're X height versus whatever. Okay, we're in the new highest column. Boom. We don't add any water. For this one, we go, okay, we're so much shorter than the previous one. We add X amount of water, scan ahead to find a column that is higher than the previous highest column. Scan ahead till we find one that is the same height or higher. We find one in this. So boom, we add our height difference, the water amount, and then go on. And we just do that for every step. We just scan from our position in the array forward every time, which is hugely inefficient. But who cares? It's correct. We're not being graded on efficiency here. First things first, we need to load these values into an array. We're going to do an 18 item array. Because we're going to go from 0. We're going to pretend there's 2 0 columns on the outside, I think. No, we don't need to do that. Okay, I really kind of need... no, we'll be fine. Okay. Let's set the stacks. Which is SDMB and SRMB. Then we'll do the loading IO. So LDA IO. And then we do... Let's do this in a loop, because that makes the most sense here. Okay. LDI 16 STAI. We de-increment I immediately, and then we do LDAIO STMI 0. Should be correct. And we'll store from 15 to 0. And then if it's not 0, actually here we need to do LDAI so we can do the 0 flag check. The simple act of loading I into A should set the 0 flag if it's 0. This is slightly less efficient than doing the decrement at the end. Really? Set this to... No. We don't. We can't do the de-increment at the end because we want to have 0 as a valid index. Because it'll annoy me slightly to waste that first byte of memory. Really? Yeah, no, it doesn't matter. Okay. We could do jump if negative. And then we just do LDI 15. Jump if not negative, I should say. Yeah, that makes much more sense, actually. Okay. This should load our values into memory. Let's just go ahead and run this. Oops. So I can make sure it loads properly. Boom. Okay. It does indeed load properly. Perfect. Now, the next step, of course, is to actually do the thing. So, it doesn't matter which direction we go through the array here. Really at all. We're probably going to want to do a recursive function. It doesn't need to be recursive. No, recursive makes no sense. We'll just call a function in a loop. We're going to need to call a function if we're doing a loop. We'll do... Oh... Let's start out... We'll call this scan. Okay, let's go ahead and set up I again. We're going to be using K to do the head scan. That makes sense. Okay. Now, this kind of stuff, by the way, is why macro assemblers are great. Because you can make a macro that would allow you to combine all these instructions into one line. So you would do something like loop 15. Then you would do, at the end, you would do close loop or something like that. Or whatever. And a sufficiently smart system could handle it. You wouldn't even need to be very smart, depending on how you do it. Anyway. Oh. Generate random labels and everything for you. Some things will. Not that I'm going to take the time to write a macro assembler for this. We're doing it the hard way. Okay. I need to have some values we store off to the side, and I'm going to have to document this. Otherwise, I will forget. So, let's start from the top and work our way down. So R5 is going to be our previous max height. Okay. And then actually R4 is going to be our running total. Or R5 is going to be our running total, I mean. R4 is going to be previous max height. And what else do we need? Okay, below the function barrier. Let's go ahead and do a scan forward function. The issue of it losing keyboard focus when you scroll is super annoying. It almost makes me want to write my own assembler for this. I wouldn't necessarily need an assembler so much as I would need a syntax highlighter. I don't feel like delving into the arcane world of Sublime Text syntax highlighting right now, though. It's not particularly complicated even so, but I'd rather not. Okay. So this is going to scan from I forward, looking for the highest block that remains. So, first things first. Let's preserve our registers. I'm not going to worry about preserving K in here, I don't think. Who am I kidding? Damn it. You might as well preserve K, it's free. Not free, but... Okay. So, now we go ahead and load up the I register. And then we store it into K. We de-increment it. And then, if it's negative, that means that it's out of range. So we just go straight to the end. Okay. Speed jump if not negative. The reason we de-increment K once is because we want to be in front of our current area. We want to scan from our current tile forward, not... We want to scan from the tile in front of our current tile forward, I should say. And so here we are looking for... what do we return a value in? I think we're going to return a value in the A register. We don't actually need to preserve the A register anymore. Because we're going to use A as our return value. Yeah. Technically, we could be using I in here if we preserved I, but I'm not going to do that because I don't want to have to preserve I. We'll just preserve K on general principles and go on from here. Now, what we want to do is we're just scanning numbers and we're comparing them to see if they're bigger than our current maximum. So we need to preserve a register so we can use for this. So let's go ahead and just use R0. Okay. So now we do we need to reset R0 to 0. So we do LDI 0 and then STA R0. It's important that we zero out R0 here because we have no idea what is set to, what it was ever set to elsewhere. The previous calls of this function may have set it to some weird value, and so we can't trust that it's going to be 0. It's always a good idea to zero out the variables you're going to use anyway. In this case, it's actually important. But anyway. So with R0 now containing 0, we can just assume what we want to do is we want to check R0 versus the value at K. So we want to do LDMK 0. So I'll load the value at K into A. And they want to do CMP R0. And then if the 0 flag is set, they're equal, which we don't care about. If the negative flag is set, I'll say whether they're not sure if we need jump negative or jump not negative here. I can never remember which way around it is. I'm pretty sure the negative flag is the one we actually care about in this case, because we're doing an unsigned comparison. Anyway, we'll assume it's jump negative for now, and if it's not, that's not. We'll want to step through the program and watch its behavior. This is why we need, also we need a macro assembler with local labels. Okay. We'll just call it else for now. I'm gonna hate myself for this later. Okay. We're going to need another label. Okay. Now, going to assume, actually, there's nothing to do in the default case. Yeah. Because the only thing we would need to do is we would need to store the current value of 8R0 if it's the new higher value. Okay, let me think about this a little bit. We're comparing A to R0, so we're doing A minus R0. If R0 is greater, then we'll have a negative value. So we want not negative. No, we want negative. If R0 is greater, then we don't want to store A and R0. So we just, if jump negative, then we continue. I just tried to set multiple cursors. That's not a thing you can do in this editor. I'm gonna forget why I called this label FL later, but oh well. All right. So this should, emphasis on should, scan forward through the loop looking for the tallest remaining column. And when it goes out of range, it just immediately returns. At the end here, we do need to do LDA R0. And when we're out of bounds, which can happen here, R0 does need to be 0, which it will be. Okay, good deal. Okay. That should work. And there's nothing about this that means it has to be a function. We could have just dropped it into the loop here, but I like splitting my code up a little bit sometimes. Makes it a little easier to read, maybe, hopefully. Okay. I kind of wish I could make this show up a different color. Oh well. Now we need to do a bunch of similar things here. This is scanning forward as well. It's doing the same exact thing, basically, just using I instead of K. But even more complicated. So we want to do here, we're using R5 instead of R0. Okay. Well, let's break it up a little bit more. Solve one problem at a time. So scan forward will get us a value that is the height forward. And it'll store it in A. Let's make another function. Okay. So we're going to call this get water height. Okay, so get water height is going to take two parameters. The height of the previous highest column and the height of the next highest column. And actually, we don't need to have scan forward externally. We can have that inside of get water height. And we know we are already storing the previous max height in R4. So we will just specify that we are passing that as a parameter. Okay. Now, first things first, we need to preserve the A register. Because we're about to clobber it by calling scan forward. Okay. So let's get the current wall height first. And we'll store it in R0. So for this, we're going to use LDMI. And then we'll do STA R0. Really, why are we doing this now? We don't need to do this now. Yes, we do. No, we don't. No, we don't need this yet. We'll need it later. Okay. So first things first. We get the height of the highest column remaining ahead of us. And then we check to see which is shorter. The highest column ahead of us or the highest column behind us. So we need to do CMP R4. And then if the negative flag is set, I need to just write this down somewhere so I don't have to figure it out every single time. We're doing A minus R4. If R4 is larger, the negative flag will be set. Yes. Okay. So now, in this case, we will use A. Really, let's just go ahead and assume we're going to use A as default. So let's do jump not negative. Use A. Oops. And if it is negative, then we do LDA R4. Okay. One way or another, A now contains the height of the shortest of the tallest block ahead of us or behind us. So now we know what our water height is, so to speak. Now we need to get our height, which we do right here. Unfortunately, we get it into A, which is unacceptable. So let's go ahead and do it this way. We store our current water height into R0. Our current possible water height. Then we do LDMI to get the height at the current block. Now, we need to do another comparison. Oops. DMP R0. And this will compare our current height to the height of... I think we need to do a... Do you want to just do a subtraction? I don't think we care about our surrounding height anymore. We only care about the difference between the two. I think we just go straight up subtract R0. Is that going to be the right way around? R0 is hopefully higher. We might actually want to hit the current water height before we scan forward. Yeah, let's do that. I was wrong about wanting that later. So we get the current water height, we store it. We get the height. Notably, we are using R4, but we are not changing R4, so we don't need to preserve it. And then we subtract R0, which is our current height, from the height of the tallest found thing on either in front or behind us. So the difference of this should give us how high the water is. Now, if it's a 0, then it's 0. If it's a negative number, then we are the new highest block. If it's a positive number, then we add that amount to the water. Finally finished that stupid quest? What, you didn't like Dig Site? Or are you talking about a different stupid quest? So we already defined R5 to be the running total and R4 to be the previous max height. We can actually modify them inside this function without creating any troubles. And this is turning from a simple function to get the water height into accidentally the whole thing. We might as well just grab this whole body and move it up. Yeah, because we have very much accidentally the whole thing almost at this point. So if it's negative, then we go to set new max height. Okay, otherwise, let's just grab this content. Boom. Boom. I hit backspace, damn you. Oh, I scrolled after I... Okay. All right, now. So at this point, if we want to set the new maximum height, the value is an A. No, it isn't an A anymore. Because we just finished clobbering A. We need to store that. We need to store A off to the side. Store it in R1. Here we don't need to worry about preserving registers because this is the top level loop. It's everybody else's job to worry about preserving registers. Okay. So here we just do LDA R1, STA R4. Yes. And then we go straight on with the rest of the loop. Otherwise, if you don't set a new maximum height, then we do add R5, which could be adding 0 to R5. That's fine, we don't care. And then we just do STA R5. Ta-da! We've added the difference between our highest surrounding and the current to our running total. Once the scan loop exits, we should do LDA R5, STA IO, and then halt. I'm going to move this down. Okay. Let's see if my brain managed to keep all that in track of properly. We load the values. This is going to be quite slow, by the way. It has to scan forward every single time. Okay. It looks like it might be working. R5 is at 16 already. It's definitely adding something to R5. And it keeps going up. Whether it's the right amount, oh, that's a whole new question. Guess we'll find out at the end. I think it's 31 already. 36. Starting to sound pretty high. I think that number seems a little high. 43. Yeah. Correct volume is 28. We say 45. Okay, why is it being so absurd? Let's just trace execution, why don't we? First of all, let's skip the load loop. Now, scan forward is a huge amount of stuff. Okay. A is 4. Yeah, okay, that makes sense. Okay, it's R0 is 58. What? LDMI 0. STA R0. No, that's not 50, that's not R0. That's oh, whatever it's called. Probably the program counter. Yeah. Register 4, program counter. I wish I could name these damn registers. Oh yeah, it even says counter. Please, game, let me name these damn things. Anyway. So that's fine and acceptable. Register 6 is the R stack pointer. We don't care about that. Register 10 is R0. Okay, R0 is set to 4. That's our current height right here. We're going from this way forward. Now, scan forward should return 6. And it did. 6 is in the A register. Okay. So now we are comparing R4. Okay. And I think I see the problem here. I have my stuff backwards. Doesn't make sense though. Yeah, we just decided to use 6 instead of 4, so this needs to be jump if negative to use A. Alright. We're back to where we were. We're comparing R4 to the A register. R4 is 0. So we definitely want to use R4. Which we do. Okay. Now, we store A to R1. We subtract register 0 from R1. And if negative, we set a new max height. Boom, which we do. So we load R1 into A. And we store A to R4. Is that right? I don't think that is right. Maybe it's right. Well, let's try running it anyway. Okay, what answer did we give? Something insane. Okay. So we're subtracting R0 from A. Here. Boom. Let's just get to that point. Okay. R1 was 0. No. R0, which is what we're subtracting, is 4. Okay. Here, let's change this to negative numbers so I can get a slightly better idea what's going on. So yes, we just subtracted 4 from 0. Which got the obvious result, -4. And also is completely useless to us. Because what we should do now is set the new max height. No. Yes. Yes, we should be setting the new max height. But we're setting the max height wrong. We're using R1 instead of R0 here. Yeah. Yeah. Okay. We got 38 instead of 28 now. Well, we're getting closer. Let's get to this point again. Okay, we're -4. Step. Set new max height. Boom. Start a new max height, which is now 4 in there. We decrement I. Jump back to scan. Okay. Let's step over scan. So the result from scan was 6, which is correct. The result in R0, which is our current column height, is also 6. So we should just go to use A. No, we shouldn't. We should use R4. Okay. And then we store A to R1. Which know we shouldn't use R4. Wait, what? Our current height is 6. Stored in R1. Doing something seriously wrong here. This code's a lot harder to reason about than real code, that's for sure. Real code. Than a higher level language. Because you constantly gotta remember, I'm storing this in this weird unnamed slot. Okay, so it's much nicer when you can have named return values, named parameters, all that fun stuff. And my brain's not used to working with assembly. I haven't really done it before. I mean, I have, but in very, very tiny amounts. So what we're doing here is we're deciding if we want to use the current maximum height or the previous. Okay, yeah, this is still okay. This is still okay. We should be using 4. Because we're looking for the blocks surrounding us, not ourselves. And we get a -2 here, which means we want to set the new max height, so jump negative. Boom. We load our 0, which is 6. And we store it to R4. And then we go around again. We skip over scan forward. Okay, so now we should be on this block, which is 1. And if we look at R0, which was where we loaded our current height, we are indeed on this block, which is 1 tall. And our scanned forward height is 6. So we do 6 versus our previous tallest height, 6. And we decide to use our previous height because they're the same, it doesn't matter. And then we store our current max height off to the side for later. We subtract our current height from our max height, 5. That's not negative, so we should just drop down. We add that to R5. Oh. That's the problem. I didn't clear the carry. And the subtract here set the carry. As a matter of fact, before we do the subtract, we probably should set the carry. I mean, carry will be set already by compare. But we just need to make sure. You always need to set or clear the carry before you subtract or add. And I keep forgetting to do that. I should do add without carry and subtract without carry instructions, but I don't want to pollute my already pretty busy instruction space. And this is a really simple computer, not a computer that's actually designed to be easy to program. But anyway, do you have any breakpoints? No breakpoints? Okay. Yay! No carry flags for the win. All right. And I got an achievement for that. We have a giant sea of blue of green. Everything has been completed. Nothing more remains. Unfortunately for you guys, that's not quite true though. I say unfortunately for you guys. Those of you who actually like this kind of thing, fortunately for you guys, let's go into the lab. Oh, I need to switch over to the Shin. Let's actually before we switch to the Shin, let's make a copy of the Shin. Let's rename it. This is the infamous later development, the Shin 16. Now, some things are going to have to be moved around to accommodate 16-bit registers. But at least the pinout is the same. Okay. Come on, scroll down. Fine, be this way. Okay. Think this is enough space? I'm going to deeply regret my life choices if I didn't. Okay, let's move this here. Then move it one up. And we can control Z that if we need more space. Okay, no, this is perfect. Boom, 16-bit registers. We have a little bit of a problem here, of course. In that we are going to have to do some other modifications, like make a whole bunch of 16-bit wires instead of the 8-bit wires. Oops. But now we have 16-bit registers. Level input and output we'll leave alone. I'm going to assume they can accept 16-bit input, but I don't actually know if they can or not. They probably can't. In which case we're going to have to do some changes to the system later. We'll probably have to actually move the I/O out of the registers and put them in a separate set of instructions to do output high bit, output high byte, output low byte type stuff. Okay. (16-bit rotate). Oops. We need to put 16-bit switches here. Okay. And we also need a 16-bit splitter. And we want... Not sure if that's the high or the low. Long story short, we only want one of those bytes though, because we're not changing anything about instruction encoding, except that we're going to change it so that every instruction is one 16-bit value. So we're going to have these two lines. Actually, why am I doing this? I just finished saying we're not changing anything about that. We'll split these lines apart somewhere else. So all these lines, except result V. Result V does need to be changed to be a 16-bit line. Is there any easy way to replace a line with a 16-bit one? Excellent question. I have no idea. Okay, well some of this stuff is going to remain 16-bit, like the flag stuff, or the flag's 8-bit, I mean, flag stuff is all 8-bit. Address and bank is going to be consolidated because the whole concept of banks is going to go away. We're going to have 16-bit unified memory. I think I'll have to think about that a little bit more. Yeah, we'll probably do... Okay, anyway. This part's all been made 16-bit except the wiring. I'm going to have to come back and do the wiring nightmare later. Okay. Then switches. Some of those wires magically changed. I'm hoping to get some more of that magic changing, because the longer I can put off having to mess around with this, the better. Okay. And you. I need bit 15 now. Because these all have to become 16-bit values. Which means that this shin flags needs to be modified. We need a new shin flags one that is 16-bit. Let's go make that right now. Okay. So the old shin flags one we don't actually use anywhere. Shin flags 2. Let's just rename. 2 shin flags. We'll make a copy of it. We'll name this to Shin 16 flags. Okay. Now, I need to change input V, which is this value right up here, to be a 16-bit input. Okay. I see they give up on displaying bits for that. Okay, we need a 16-bit quality. And we need to do this to check bit 15. The rest of these values can remain 1 and 8-bit as needed. Because we're just checking, this sets the 0 flag and this sets the negative flag. Okay. We need to go down and delete all these shin flags thingies. And we need to add in Shin 16 flags, which should be somewhere around here. There we go. How many of these damn flags blocks did I use? A lot of them, apparently. Come on. Okay, that should be all of them, I hope. Boom. All right. We can still use the good old Shin register load select because you have the same number of registers. 4-bit decoder is still good here. 4-bit muxes are still good there. Except, these need to be 16-bit aware. Okay. We need to go make a copy of the good old 4-bit mux. Okay. Okay. Now, we need a 16-bit switched output. If I ever named these outputs, I regret it. Because I'm not going to name them now. You can't read the names anyway. Oh, we need to do the 2-bit muxes too. Okay. Okay. Let's just go ahead and delete those. So I don't get confuzzled later. And then we go switch schematic, 2-bit mux, duplicate, rename, rename. And we're probably going to have to do a 1-bit mux on top of that. Nope. Okay. Place 8-bit switches with 16-bit switches. Replace 8-bit inputs with 16-bit inputs. I don't even remember what museum kudos get you. Let's see. Output, we want switched output. 16-bit. Go. Okay, we need to swap all these wires too, but I'm just going to cross my fingers and hope it works without me having to. Who am I kidding? Of course I'm going to have to. The longer I can put off having to redraw all these damn wires, the better. Because, like, sometimes this game will just randomly decide a wire should be blue instead of, or, you know, it should be a different bit width than what it's supposed to be. And I'm kind of hoping that will come save me here. Like, if your wires get crossed in a certain way, they'll just burn. Like this one. That wire is absolutely not supposed to be an 8-bit wire, and yet. Hello, Treebeard. I'm gonna just check to see if I'm missing something here. Let's see. Yeah. I don't think there's a way to do that. 6 levels away from 700? How the last 2 levels are going, Treebeard, is that we finished them. Now I'm upgrading the Shin to be a 16-bit computer. And right now I'm contemplating that I'm going to have to change all of these wires one by one to be 16-bit. Oh, sucks to be me. Well, I'll not go faster. It won't affect the speed at all. Except maybe make it go slower. It shouldn't make it go much slower. It might increase gate delay a little bit, which is why it might make it go slower. But what it should do is allow me to more easily access memory. Because then register width will be the same as the memory address space. And having register width match address space is kind of important for the next stage. Okay. Oh man, redrawing these wires is gonna suck. Okay, where's the damn 4-bit mux? Okay. Oh well. So these 4 wires need to be 16-bit. These wires all need to remain 8-bit. This wire needs to go 16-bit. And these 2 wires get replaced by a single 16-bit. And unfortunately, there doesn't seem to be a way to just upgrade a flipping wire. Oh well. I wish I could just click on a wire and upgrade it and everything it's connected to 16-bit. You know, all the wires that are connected to it. For now, I'm just replacing all the components. These are all remain 8-bit. That's fine. This gets switched to 16-bit data width. Which means this needs to become a 16-bit switch. And also, importantly, we're going to store our programs in RAM from now on. So the dual RAM functionality actually is going to matter. Because the Shin 16 is not going to use the program block. Not really. Well, we can switch it to 16-bit. But we're going to have a bootloader that loads the RAM, or loads the program into RAM. So PC is no longer going to run to here, PC is going to run to here. When we get to that point. And also, the ISA is not going to be wired directly to this, it's going to be wired directly to the RAM. I think we can use the same ISA mostly. For now, we're not changing it. We're just upgrading everything to 16-bit data width, where it matters. The flags are still going to be 8, which is going to be interesting. Anywhere that bridges a 16 to an 8 is going to have to be modified slightly. And vice versa. Okay, what else haven't I changed yet? These are all 16-bit. That's all 16-bit. This is mostly 8-bit still. That needs to become a 16-bit adder. As does that. Boom. Okay, 8-bit switches go there, there, or 16-bit switches, I mean. Did I say 8-bit switches? I mean 16 if I did. 16-bit NOT goes there. The rest of this is all 1-bit stuff and is therefore correct still. Okay. These are the jumps. They still use flags, which is staying 8-bit for now, because we do not need 16-bit flags. Okay. This register holds the halt reason. We might as well make that 16-bit. Not that we actually use the halt reason for anything, it's just because we have to provide a parameter to halt because of the way the computer works, so. Okay. Need a 16-bit adder. What is this section of the computer again? This is the jump section. Which means this is implementing... Oh, I don't remember what instruction this is. Something or other. This is all 1-bit logic, that's fine. This is the address logic. So we need a 16-bit adder. And we need a 16-bit constant. Which is a bit of a problem because it doesn't quite fit. And this needs to be set to 1. Because we're no longer incrementing our RAM space. No, we're not doing that. Yes, we are doing that. I wish the dual RAM worked a little differently than it does. Because real RAM is byte addressable. Almost in every computer that's ever been. Which means if I ask for a 16-bit value out of here, what I really should get is 2 adjacent RAM locations. What RAM options do I have? Like this RAM. So this is completely wrong. It should be using 16-bit pins. Or 16-bit wires, I mean. Why is it like that? Whatever. We have a wire here we can connect to when the time comes. I don't know if I pass in Okay, do these spots still hold bytes? Or do they hold 16-bit values? I hope these still hold bytes. Because then it would still be correct to use 2 as my program counter. Like if I set this to use 16-bit data width, edit the program, let's type in add R0. What's that give us? 24, 10. Okay. Is that bytes still? Is it outputting a 16-bit value here? Let's try something. I need a 16-bit thingy before it'll let me draw a 16-bit wire. That is annoying. Okay, so this is outputting 21. That is exactly what I did not want to see. All right. So this needs to be left to 8-bit address. Or 8-bit data width, for now at least. This leads to a little bit of a problem, because here we only have 2 outputs. I need more than that. If I want byte addressable RAM, which we're not going to have byte addressable RAM, I guess. Because I do, if I have unified or non-unified, if I have unified memory, which I am going to be moving this to unified memory, because I have to, then there's no real way to have byte addressable. Yeah, it's... Also, this is really bad. Because if I change this to 16-bit data width, then each one of these turns into a 16-bit value. That's really bad. Really, really, really bad. We're not going to be able to use the program block. Which means... I mean, we can use the program block, we're just going to have to combine stuff together. And I don't know what happens if I add too many instructions. How many instructions can I add? Actually, here, wait. Let's just put a whole bunch of... Well, there's 8 bytes right there. What I want to find out, can I go past 256 bytes? Yes, by a lot. Okay. Are those bytes addressable? Let's find out. Okay. Let's go ahead and feed in a 16-bit constant. Let's say 512. And we get 2137 out. Why'd I use names here? Let's just... Boom, 6432. Okay. We're getting 64 and 32 out at address 512. What happens if we change to address 511? 464. Okay. So I was trying to figure out if this is byte addressable. It is byte addressable. It is outputting... Okay, so this can hold an unlimited number, apparently. We are not limited by how much. Now, experiment with a RAM block and figure out if that's going to work. The important thing is, though, the program block is not limited by its byte width, so we can use this still. That is a huge relief. As long as we leave it to 8-bit width and combine two wires together, it'll still work exactly the way it's supposed to. Alright, good. Now, the RAM blocks, on the other hand, well, who knows about those? We need the dual load RAM because we're going to have to address it twice each cycle. Once for the program and once for the... I'll call it. Okay, and let's grab a 16-bit switch just for some place to connect things to. Okay. Now, 16-bit constant. We want data width 16-bit because we need 16 bits coming out of the outputs. Okay. We want a 1-bit on. We can enable the load pins. Here, wait. Yeah, that's the save pin. That's the address. Load pin, address 2. There's the save value, which we also want to provide. Okay. Let's just leave those on all the time because we don't care about. Okay. At address 1, I want to save a 5. Actually, would save something too large for a 8-bit value, so 512. Boom. Okay. That's good and bad. Each of these columns is still 1 byte. However, it is not byte addressable. Damn it. It's annoying. I could half the clock speed. And use a single load RAM. And do load the instruction, execute the instruction, load the instruction, execute the instruction, load the instruction, execute the instruction. But that would be kind of obnoxious. I think we're just going to have to sacrifice byte addressable RAM if we want to do that. Yeah. Their alternative is fast RAM, which I'm pretty sure we just leave data width to 8. And then we just read 2 bytes. And combine them into a 16-bit value. If I half the clock, okay, where am I even getting the clock anyway? The closest thing we have to a clock is this counter here. If we replace PC with a count, if we don't use a counter for PC, and instead we use a counter as an actual clock, is there a clock chip somewhere? Just a simple... We could make a simple 1-bit oscillator and use that as our clock. Stop using a counter for PC. And then just on the even ticks, we load one thing from RAM, and on the odd ticks, we load the other thing from RAM. I think that's what we actually should do, because I don't want to give up byte addressable RAM. I know unaligned memory access is a terrible idea. I want it to be a possibility. It's more realistic, damn it. So let's go ahead and build our clock circuit over here across from the RAM. Let's remove the dual RAM. Boom. Sorry, dual RAM, you need to go. Let's install fast RAM. We're gonna have to make the RAM system a lot more complicated. Because every other tick, we need some way to get the system started too. let's leave this alone for now, while I think about how we're even going to start the system. Because I need something that's going to inject a single pulse into the system. We're going to need a switch that turns itself off. Through a delay line. Except... no. Let me think about this for a second. Yes, maybe... okay, so what we need to do... we need to have a circuit. Oh, I know how to do this, I think. Where is that 1-bit mux? There we go. Okay. We fix one side of the mux on. Where to go with that delay line? Get back here. Boom. Next tick, it switches outputs. And this should oscillate forever. Every tick, we get a different value out of here. Okay, so we've made an oscillator. That's what we needed. So this is the system clock. Basically, it's a tick divider in this case. And then what we need to do is every other tick we load. We need to load. Okay, we need to make a system here. Let's do this over here. We need to make a system. Effective, we need to make a dual RAM. That is 16-bit, but is byte addressable. So I think we actually should do this in the component factory. Okay, new schematic. Let's call this (16-bit) dual RAM. Okay. Actually, I should rename that. And clock. Because it does contain a clock as well. And that is actually going to be important because it's going to drive the computer. Okay. RAM. Need fast RAM. Okay. I/O. We need 16-bit switched outputs, 2 of them. We need a 16-bit input, 2 of them. And we need 2 1-bit inputs. Okay. There's the address. Let's go and do... Oh, I don't know how many bytes you want to set this to. 2048 for now. Data width must be left at 8 bits. That's how we get byte addressable. And we need a 16-bit maker. Actually, this isn't quite right. Do we have a 16-bit delay line? Yes, we do. Okay. So one of these outputs needs to be connected to a delay line. And the other output's raw. And actually, one of the outputs should be switched and the other should not. What we want to do is load every other cycle. I think we actually need another 16-bit input. Okay, let's start naming these things. This is PC, the program counter. Did I provide an 8-bit output? Or a 1-bit output, I mean. This is clock. When this is high, things should happen. Otherwise, wait. System should do nothing. We have to start with clock low because we need to prime the memory before everything works. Okay, this is PC. This is address. That's store. Okay, you are output, and you are instruction. Okay. You are load. And you are store. Now, we need to put switches on these. We need a mux. And these get run into the address line. Okay. Let me feed this to the clock. All right. So it does properly take PC first. That is good. Next tick, it will take from address. So when PC is on, what do I do with 1-bit mux? We don't need to have switches on these, we need mux. Switches can be used for a mux, but... Okay. Boom. Okay, when these are on, they're fed through. When they're off, okay, that's perfect. That'll match up beautifully with our existing clock. And then these values are known ahead of time. So this is store. That is load. Load is always energized. Store is never energized. For PC. Okay, and you just go straight to there. Now, these are 8-bit wires. Okay. And then we need another 16-bit mux. No. We need the opposite of a mux, which we don't really have. Let's go ahead and put a 16-bit maker on there. And then grab a pair of 16-bit switches and put one there and one there. Out just a little bit. Dot gate there. You energize both lines. And this either goes to delay line or it goes to straight output. Okay. Now, lock next to this. That is fast backwards. Yep. There we go. Lovely. write the program counter value to the delay line, and then next tick it should output. Additionally, we need to hook up one more wire. If we are calling for a load, that needs to run to there. Also, this wire needs to go to there, because this is the doubly inverted clock, so it's, in other words, the clock. And additionally, we should only allow this thing to enable when the clock is high, so we don't get the load value from loading PC. So when clock is high, this could possibly or could not be possibly outputting. Also, I should probably make PC a switch to output as well, I guess. That way we only output when clock is high. And it drops to 0 otherwise, between cycles. Okay. And we'd only need to make a few tiny changes to get this thing so it doesn't look quite so stupid. First of all, let's just add some offs across the top. And there we go. Remove you. And we have a 16-bit dual RAM and clock. And I'm tempted to move the output circuitry outward. Make this thing long enough for its whole name to fit. Except the way the chip zooms out is going to make me regret that decision. Oops. What? There we go. They make it super hard to read. Oh well. There. Lovely little chip. I would kind of like to move all these pins up one step. But if I do that... Well, you know what? Let's do that. We're not going to move just the pins, though. We're going to move everything up one step. Here, let's get rid of these temporary bits. Actually, okay, let's move just this much up like that. Okay, that's actually not terrible. Okay. Lovely. Now everything's centered up. Looks nice. Wiring's not incredibly bad. Yeah, we should have byte addressable memory. Do some testing here. Set address to 5. Let's set store to on. Set value to 10. Or I was just 12, that's fine. Okay, 1 tick. 2 ticks, boom, value set. Now, if we set address to 0 again, we should oscillate between 0 and 12 in this line. Especially if we turn store back off. And our values on the outputs oh, this can't be. This need to be wired to the clock, not to. I mean, this needs to be wired. Okay, this needs to be wired to the clock. Like that. Okay. And it probably erased my value memory? Yes, it did. Okay. That's annoying, but not a big deal. Alright. Set you back to 5. Store on. Value still 12. Pick. Set. Turn store off. Set address to 0. Pick. Boom. It outputs 12, 0. Okay, if we turn load on, pick 12 and 0. Okay, that is working. It's energizing the outputs together with the clock when load is set correctly. Okay, good deal. I think this will work. Back to the sandbox. And delete that component. Where is 16-bit dual RAM and clock? Okay. So this gets us result V. Okay, this is actually okay. There we go. Now, this is store, which we draw over to memory here. We need to delete these pins. They're in the way. Gets drawn over to memory store. This is load, which gets drawn over to memory load. This is value, which gets drawn over to memory V. And then we have address, which gets drawn over to ADDR. Bank gets discarded. It's no longer required. And then the top one is program counter, which is going to have to go on the stack from now on. This switch... What was that switch used to... What did that switch used to hook to? Memory load? No. Yes. No. Maybe so. Yes, it used to hook to memory load. But I don't think we need to do that anymore. Why did I have a switch there? Let's load up the old Shin ISA and take a look at it. Did it load me into the old Shin? Yes, it did. Damn. Wait. Yeah, screw it. We'll redo it from scratch. It's not gonna be that big of a deal. Okay. Oh, this one didn't have a switched output. That's why we had to switch here. Okay, I see. Okay. Switch to the Shin 16, damn you. There we go. Yeah, we no longer need that switched output. The bank line can go away, because bank is no longer a concept we need. In the same vein, require bank is no longer a concept we need. Which means we need to work at that from the top to the bottom, or bottom to the top. Okay, anybody who was talking to require bank is going to have to be disciplined. And their bank privileges will be removed. Okay. Similarly, anyone who is actually writing to the bank register, or any had bank registers of their own. Oh, look here. Here we have bank registers. Guess what? They don't need to exist anymore. Except it's not quite that simple because we use this code for other things as well. Okay, that's a dead wire now. We just keep trimming wires back till we find wires that are actually used for something. Okay, that one does nothing. Okay, this one goes to DP. And that goes to RP, so this part over here is still used. Means this ore is used, and these are still used. So this segment is still used, but it no longer serves the purpose of powering the bank registers anymore. Because we don't have bank registers, we have stack pointers. Okay, so we can continue exterminating bank now. Okay, this talks to require bank, which we no longer need because we just have an address now. Yeah. These need to be 8-bit, or 16-bit, I mean. Oh, think of all the fun bugs that are going to be in here. Things that I forgot to upgrade somehow. Those all need to be 16-bit switches. Thankfully, most of the 16-bit components are the same size as the 8-bit components. Otherwise, I would be tearing my hair out. Okay, there's a big old block of 8-bit components here. Okay. Oh, that was just adding one. That's why it's set up that way. Oh, it's subtracting one. Okay. These need to be changed from 7 to 15. Okay. Now, the switches. Some of these switches might not need to be changed. Okay, like ARG3 select, that's still an 8-bit value. So these remain 8-bit. The rest of these, though, are ARG1 through ARG3V, which do need to be changed for sure. Okay. I should have done the wires first. Okay. Those negates need to be changed. Why am I negating before and after? Okay. 16-bit mux goes here. Are there any other mux? I don't see any. Boom. Okay, are there any 8-bit? There's another 16-bit switch that needs to go in there. Any more 8-bit parts? I need to be replaced. Doesn't look like it. Okay, we're good. Those are 16-bit already. This part is 16-bit already. There's an 8-bit switch that got missed. Okay. Okay, now. That's all 16-bit. This is all 16-bit. Okay. What about you? You're still an 8-bit. Okay. Boom. Get with the times. Okay. I do believe that we are very nearly done with the upgrade here. Okay, this counter is no longer needed for PC because PC is not going to be handled by a counter. However, what we do need to do here you directed into the load. And let's see, PC is... Okay, let's select this. Move it up 1 to indicate that it's a special register. Same way that bank used to be moved up 1. We'll decide what to do about bank later. Because bank is no longer a concept that we need. I should go back to continuing to exterminate bank like I was doing before. Okay, here's bank required, which turns on the load for bank. Okay. We actually want that register to be wired in normally now. It's no longer going to be a special register. It's currently unnamed. It's still called bank, but it no longer serves its purpose. We will change its name later. Okay. What was this? It has something to do with this register, which is register 4, which is the flags. Or register 3, I mean. This is the flags, okay. This is the flag refresh circuitry. The flags is stored in a delay line instead of a register because that made sense at the time? Question mark. Okay, so this is PC. And we now need to load select PC. We don't want to load select PC. Well, we need to load select PC, but we want PC to be load selected at all times. Boom. Because we do need PC to be a constantly energized wire. Okay, so that was the only people who talked to bank. Alright. We can consolidate the bus slightly. We do need to add some more stuff to the bus, but not in the memory section. Let's go to the bottom. Grab memory load and address. Come on. Making changes to the bus is such an annoying process. Okay. And then we do the same thing again for the address line, which we're going to have to end up replacing with a 16-bit line here in a second. I don't know why I'm bothering. In fact, a lot of these lines are going to have to be replaced to the 16-bit line here in a second. Okay. Now, flags V, flags set, flags used are fine the way they are. That needs to be 16-bit. The value lines all need to be 16-bit. Why did I do that? I know better than doing that. Okay. Okay, there we go. The result lines all need to be the value argument. Okay, the value lines all need to be 16-bit. The address line needs to be 16-bit. The instruction decode lines should all be 8-bit. No. Yes, no, maybe so. Op select can be 8-bit. Problem is these can also bring in constant values. Unless I want to limit constants to being only 8-bit. I guess I could limit immediate values to only being 8-bit. Makes sense. Because you can't specify a bigger one anyway, because we only have 16-bit instructions. And only 8 bits of that are for the argument. But yeah, these can all be 8-bit. If you want to load a larger constant, you'll have to do it in 2 steps. Okay. Name these wires. Currently, we're not changing the ISA at all. That's not realistic. We are going to have to change it. But we'll get around to the changing part later. For now, let's just redraw the upper part of the, we're gonna call it here, of the bus. Let's just keep working our way down, redoing the bus as we go. Okay. I'm not quite sure how we're going to handle clock yet. Oh, it's going to be a nightmare. Like the delay line system we're using to hold the flags, we're going to want to change that over to a register system because otherwise we're going to have to cycle the clock or cycle it based on the clock. Let's insert the RAM before we forget to do that. Matter of fact, this is perfect. We have just enough room for the clock wire. We'll run clocks right beside flag. It'll fit right in there. Okay. Now, this is PC, which we currently do not have PC on here. We'll just run it over there. This is ADDR. Boom. This all needs to go down one line at least. Boom. Okay. Oh, memory V needs to be... Okay, this is result V. That's clock. And this is the instruction. Okay. Boom. Shorten that up a little bit. Okay. This is memory V, which also needs to be 16-bit. Somehow I missed that. Yeah, I just called it memv. Okay. Because this is the value going into memory. In other words, that line right there. Memory load, memory store. Okay, RAM is hooked up. Oh, now. Continuing. Grab new documentation sections. Boom. What happens if I paste in 16-bit over top of an 8-bit wire? Does it ignore it? No, it upgrades it. Ooh. Tasty. That'll save us a little bit of time. I won't have to delete the documentation stuff after all. You just paste the new bits over top of the old. Okay. Now, back to the top. Draw a new wire. Draw a new wire. What happens if I draw a new wire? Or green, blue pin. Okay, it just doesn't do the thing. We do need to delete those wires and replace them. Boo. Boo, I say. Okay. Damn it. All right. We have to upgrade the wire every step of the way as we go. Go ahead and upgrade results. This is an 8-bit MUX. That needs to change. Oh, an 8-bit delay line needs to become 16-bit delay line. 8-bit switch needs to become 16-bit. Yeah. Actually, no. Flags remains 8-bit. The problem is we need to energize this not only when flags used is on, but also when, this needs to be energized when clock is off, as well as when this is off. So we need a NAND gate, I think. No. We want it when both inputs are off. Let me think about this for a second. So we want this to be energized, in other words, refreshing the delay line. When I should just make flags 16-bit. No. Yes, no. Yes, no. Yes, yes, yes. No, no, no. Also, the constant engine needs to be made a little bit more complicated. I'll think about it. But this, when clock is on, this switch needs to be on. Or when clock is off, I mean. No matter what. When this is on, this switch needs to be off. I think a NOR will work. A NOR should work. Okay, so we're okay with this being an 8-bit value for now. Okay. Now, flags works fundamentally different. Also, we need a 16-bit splitter. I don't have room for this. Okay, all this stuff needs to be moved over one spot. We do have room to do that. Not you. No. There. Boom. 16-bit splitter. Output 1 is this one. That should be the right value. So we write the low 8 bits to the flags. Not sure why I'm bothering to keep flags 8-bit. I'm just doing it because the alternative would be more of a pain in the butt. These two switches need to be 16-bit switches. These are... Okay, that's annoying. Okay, these are the stack pointers right in here. Okay. We're going to have to do something different about input. I'm pretty sure input comes in 8-bit. For now, we'll just rig it up to the 16-bit, though. What's the worst that can happen? And then the general purpose registers are delightfully uncomplicated. Okay. I might actually make bank if I move all this stuff down one. Make bank register, basically take up the space that bank was consuming. I could have a register A and register B, and then that would be the register B would be defined as the destination for multiplication. Because we're freeing up some register space. And if I move IO to its own set of instructions, which I might, that'll free up some more space. Yeah, I don't know. I have to think about it. Okay. The constant engine needs to be modified slightly. Okay, these need to remain 8-bit. That's correct. What is changing and an awesome twist of fate, we have enough space for this event. Is that the outputs are 16-bit with 0-byte high values, or yeah. Okay. Now, on to the next line. Do the next two together because I'm pretty sure we've gotten all the cases that actually tie into these lines in this block. updated. That's not to say everything is updated yet. We're far and away from having everything updated internally. I need to go fix the rest of this block before we move on. Oh, I'm not looking forward to this part. Okay. This is going to be unfun. Because we have a huge block of interlaced wiring here. And I need to redraw all of it. The good news is that, as I discovered earlier, oops, I can paste wires over top of each other and have them override the old ones. If I do this, that gives us beautiful 16-bit wires right there. And now, I just need to replace all of these wires. What? Oh, that's interesting. 8-bit wires are still there. Okay. That's an interesting bug. Or at least a buggy behavior. Okay. Go. I'm gonna keep wanting to drag all the way across, and that's not how this works. Okay. Now. Go ahead and hook all this up. Program counter. Yeah, which wire was that? This one. We are going to want to confirm that is actually the program counter. Yes, it is. Okay. Okay. Now, we've got a bit of a problem here. Because this delay line is 8-bit. It needs to be 8-bit. Here, wait. We've got room for this. (16-bit) maker. Boom. Boom. Okay. If you ever ask for the value of flags, we can get the 8-bit value out as a 16-bit value. Just like that. Makes the wiring a little bit messier, but oh well, you can't help it. It can't be helped. Well, it probably could be helped, but I'm going to regret doing that, aren't I? No, I won't. This was such a pain in the butt to draw in the first place. Okay. Thankfully, most of this part is very standard and straightforward. There we go. And this last connection. Ta-da! The internals of the register system are now properly 16-bit. These are still 8-bit the way they're supposed to be. Yup, okay. That's still 8-bit. These are all 8-bit to 16-bit. Exactly as designed. Okay, everything in this section is done, I think. Okay. Okay, that line is now 16-bit. As we convert our way down, we will get around to hooking into that line later. All right, now this section. This does not deal with memory. Piece of shit. I hate this so much. All right. I wonder what happens if I switch over to Overture and then switch back to Shim 16. I think it... Nope. It did not remember any of that shit. Matter of fact, it did quite the opposite. It wiped out... Okay. Let's just go ahead and make a copy of a known good documentation line. And let's redo all the documentation lines entirely across the entire system. That way there will be no weirdness. Just go 64-bit and be done with it? No. There's no reason to go anything larger than 16 in this system. I probably would go 64-bit if I was designing this with if I was just writing a virtual machine, I would just go straight to 64-bit. But as it is, there is no reason to do it that way. Okay, now we're doing this section. The flags are still 8-bit. Result V needs to be 16-bit though. I already made that switch 16-bit. Why is there a pin there? Also, flags used is flowing the wrong direction here. There we go. Not that it really matters, but I want everything to be flowing from top to bottom. Okay. Oh, I see. We can't drag off that. Okay. Should be correct. The basic move circuitry has been completed. I do believe. Oh, that's why. I was like, why in the world are we setting the carry flag? Because the carry flag is part of this instruction group. Okay. I had forgotten that again. I keep forgetting that this is move and set carry. All right. We actually need to redo this. Because I don't want the 0 instruction to do anything anymore. That should be nothing. Because the instruction line is going to read 0 when the clock is low. And I don't want to put I don't want to put clock handling in here if I don't have to. So we're just going to re-encode it. That first 0 instruction is nothing. The bank 0 instruction 0 do nothing. I need to make a note of that in here because when we go in to fix the flags or fix the ISA, Damn it, how many times can I spell nothing wrong? There we go. Apparently the answer is several. Okay. Go ahead and drag all these lines into place. Step at a time so we make sure we don't hook anything up to the wrong thing. Okay. We don't really need documentation lines there. Because the documentation lines are right here. It's not like it's a grand mystery what connects to what. Okay. And clock remains unused for now. We're probably going to end up having to tie a bunch of things into clock to read if the computer should do anything or if it shouldn't do anything right now type stuff. A lot of things are going to be turned off using clock, I'm guessing. Know what I'm saying guessing here? Because I'm not actually sure. Okay. Boom, move this down. Okay. Get the memory lines hooked up for the next section. These are 18-bit switches, 16-bit switches already. That's good. This goes nowhere. This goes to the flags. This is strictly to check for if it's 0 or negative. So it doesn't actually. We already modified the flags block to take 16-bit values on that. Okay, arg3 select remains 8-bit. Because the select stuff, well, due to the way instruction decoding is going to work, or instruction encoding, for that matter, it makes total sense to just leave it alone. And it would not make sense to change it. Okay. Okay. That's annoying. Guess we could do it that way. Now we need to do the internal wires. Like that. Okay. No, we can't draw from that because it doesn't know how big to make the wire. Let's trim these wires. Those two don't go anywhere yet, if they ever will. Where does this wire go? Where was it supposed to go? That's an interesting question, actually. What is it doing? Attaching to a multiplexer that switches between Okay, we need to load up the unmodified Jin computer to see where that wire went, if it went anywhere. Oh, that's the address line. Okay. For some reason it became disconnected. Okay. Yeah, okay. That actually makes perfect sense, because it just goes that way. Alright. Okay. I do believe that is the push and pop engines finished. Actually, wait, no, those are 8-bit. No, they're not. I thought they were 8-bit because of this has to be an immediate value, but then I realized no, because we're getting it from the wrong line. Technically we should be getting it from the argument line, but that's not provided, so we're just grabbing it from what is available. Okay, let's draw in the clock wire and go down to the next level. Alright, address. This is memory value. No one else talks to address here. No one else talks to memory value here. It was easy. Okay. Why did we not have hooked up? Oh, this is the jump engine, which means it doesn't set 0 or anything like that. Okay. That would explain that. I'm glad I ran my wires neatly and straight, because otherwise I would be going insane right about now. Okay, these are 16-bit multiplexer. That should be a 16-bit switch. Okay. There's no reason for that wire to go out that way. Flex needs to be hooked up. That adder needs to be hooked up. Okay. Oh, this needs to be changed back to 2 again because I went back to byte addressable RAM. I spent a whole bunch of time making byte addressable RAM. Technically, we could have variable size instructions now. Wouldn't that be a fun idea? Okay, flags. This stuff gets left alone. This stuff definitely does not get left alone. Oops. Okay. It's tied to there. All right. That's another block finished. Lovely. Oh wait, we need to draw the clock wire through it yet. I have no idea if this is going to work properly. It should, you know, without having to hook the clock up. It should. As long as the no op instruction is implemented properly. The computer should just set, do nothing. Because we did put this little bit of code in to check. I'm going to change this slightly. I like the way that looks better. We put this in to keep the flags energized through a no-op cycle. Because due to the way our RAM is working, we're no longer using a counter for PC, which means I need to do some stuff to take the PC up by 2 every time. Probably should do that here, maybe. Well, we'll do that later. That we're going to need the clock wire for. Okay, this block does not deal with memory at all, so we can just draw those wires right on through. Matter of fact, I don't think any blocks below this point deal with memory. At least not yet, currently. Okay. Apparently argument 3 isn't much used here either. Oh. Go ahead and trim these ends. There's no reason to have that stuff sticking out anymore. We've pretty much decided how the shape of everything. I might want to add more instructions to the ISA later, but I almost certainly will. For example, I probably should separate, I don't want to do separate instructions for IO operations instead of having IO be a register. Although IO being a register will still work for now. I might need to do something, I don't know, we'll see. If it turns out it doesn't work, then we'll mess with it. If it just works magically, we'll just leave it alone. Okay. Everything is 16-bit that needs to be 16-bit? I do believe so. Onward and downward. Let's just trim that off. We'll leave these sticking out for now, just in case I want to add more instructions. It'll make it a little bit easier. Okay, once again, argument 3 isn't used at all. I think we're going to use exactly the same ISA format for the Shin 16 as for Shin. And we might even just go straight up, make copies of all the Shin ISA blocks and just rename them. That way I can modify them without worrying. Well, I'm definitely going to do that. When we get to that point. Oh. Where did you go? You were important flags value. How did you get deleted? No, this is the carry. We don't use the carry down here. Yeah, we don't need that. That's a relic from copy and paste. Yeah, let's just remove that. And also, this is argument 1. That is argument 2. We should always feed argument 1 in first. Which we already do for the adders, because otherwise it'd be backwards. Okay. This is now almost 16-bit compliant. Go. What is? Definitely become a little faster as we go. Particularly for these sections, which are largely copy and paste of each other with just slightly different operations inside them. Okay. Now, argument 1. Hello? Well, be that way then. Oh, the shift amount is still 8 bits. Okay. Well, we don't have 8-bit values, so we're just going to provide them with 16-bit values. Okay. Let's just do a quick check here to make sure I'm not... Oh! Hello, Noms! Welcome here. Bringing all your little lunatics with you? Welcome, Raiders. Welcome, welcome. I hope you people aren't going to be too bored of, well, if you're doing game dev, you shouldn't be too over everybody's heads with this then. Have you seen this game yet? Because this might be something you'd like. I'm currently expanding my 8-bit computer to be 16-bit. We've got our RAM up here, and then we've got registers, instruction decoding, various bits of the instruction implementations themselves. It looks much smaller than it actually is because a lot of these are, all the light green stuff is custom chips. Like this bit right here is a custom chip that contains multiple other custom chips. It's basically a really fancy circuit simulator. And the best part is, it starts you out at the very bottom, learning about how... Oops, here. That's not what I wanted. There we go. Starts you out at the very bottom, learning the very basics, how a NAND gate works, how to make a NOT gate with a NAND gate, how to make other different kinds of gates with NAND gates, how to do arithmetic with gates you've made, how memory works, putting together a really super basic working computer, how to program that really super basic working computer, how to improve that working computer, how to improve that working computer even more, and then a bunch of programming challenges using your own self-designed working computer. It's pretty cool. Your brain hurts? Oh, come on, don't be like that. Everything is in little tiny steps, so it's really easy to pick up. Okay. I want to do a shift left. This value, I think. By. I'm just checking an assumption here to see if it's true. 8. Boom. Okay. That is correct. And if we take a 16-bit adder, I totally don't need to do at this point. We will get our input value back out as the output. Okay. So I was correct that output 1 would be the low byte. Output 2 would be the high byte. That is all I needed to know. Probably don't need to actually split these down to, because it'll automatically take the low 8 bytes, or 8 bits. I have confirmed that before as well. Well, see you later, Noms. Poor survey. Don't worry, survey. We're almost done. Okay, now. Speaking of almost being done, I think I'm almost done converting this to a 16-bit computer. Yeah, it looks like we've got the whole bus done and we've converted the blocks as we went. So now all that's left is to fix the ISA. I think. And to fix the memory subsystem. No, I don't want to hook that to there. Kind of did want to hook that to there. Okay, let's delete the PC line. Oh, I need to make PC count up, don't I? I didn't do that yet. Okay, PC is connected. It does not count, though. Like, literally, it doesn't count. We'll move the program block over here somewhere. We will leave it right where it was. Yeah, we'll leave it right where it was for now. Oops. I don't want 16-bit for this, I want 8-bit. Okay. We need a 16-bit maker. And that will get us our instruction. Okay. That should be correct. This instruction needs to run to the bootloader. Because I need to be able to load this program into memory. Okay, let's make a new ISA chip. Duplicate that. This is the Shin 16 ISA. Can I drag these into a folder somewhere? Okay, will not let me drag those down. Did I accidentally just drag? No. Okay, we're good. Is there any way to select multiple? No, there is not. Well, that sucks. Well, let's put all the stuff that is specific to the Shin in the Shin folder. Might be a little bit premature. Okay, Shin register load select. And we need to make a Shin 16 flag or folder. Wait a second before I do this. Oops. Can I duplicate a folder? No, I cannot. Damn it. That would have been so slick. Alright. Shin 16. Which we put the Shin 16 flags into, and the Shin 16 ISA. Okay. We'll just go ahead and put the dual RAM and clock in there as well. But yeah, div is the one that doesn't do anything. Okay. Select IO bank isn't used anywhere. It must have been something I made for leg and then never used. Alright. We are definitely in Shin 16 ISA. So, I now want to modify this slightly. That these two pins are a single 16-bit pin that we will call instruction. Input, 16-bit input. Okay. Then we take a 16-bit splitter. Okay, op select. Okay, this is op right here. That's perfect. We just hook output 1 to op. And output 2 to arg, and that should be exactly what we want. Okay. Now. I want to make a copy of this entire block. Right like that. So we have plenty of room for the B group. And then we will grab Shin. We want 4B. And that slots right into the 4 slot. We'll leave the template out of that. This is where 3 would go if we had a bank 3. Bank 3 is a historical relic that currently does not exist. Once upon a time, I don't even remember what I was going to store in bank, what instructions were going to be in bank 3, but they were removed and never re-added. Okay. Now, technically, most of these ISA blocks can probably be left alone. However, I want to make copies of all of them. Custom component cannot be used as it has no area. Oh no. Switch schematic. Up a level. Go into Shin. Duplicate. Rename. Shin 16 ISA 0A. Move it up a level to get out of here. Go ahead and make duplicates of all of these. Okay, and then any of these that are named 2 get renamed. Which should be simple enough. Might actually get to some actual programming today. Some more actual programming, I should say. Considering we did finish the last 2 puzzles earlier. Okay. We're still using the Shin register load select in the Shin 16. Not a problem. And the only reason I'm making a copy of the Shin 16 ISA template, or the Shin ISA template, is because I want it to be available in the Shin 16 folder. I have to go hunting it. Probably should make a copy of that register load select just so that I have all the things that are used by the Shin 16. Alright, let's do that. It'll be completely identical to the Shin register load select, but it's somewhat important it's different, I guess. Okay. Just go ahead and drag these in. Thankfully, they allow you to use the scroll wheel while you have the mouse button held down and you're dragging something. Otherwise, I would quickly go insane. Okay. Stack's not used by anything, right? Yeah, that was a terrible idea in the first place. Okay. Now, oh, thank you very much for the follow, Gladius88. Really appreciate it. Pin 16 ISA 7A goes there. 6A goes there. 5A goes there. Technically, any of these slots could take any of the ISA pieces, but they're in order because... Okay. Wait, that was 4B, wasn't it? Yep. 4B goes up here in the B bank. 4 is the only one that has a B bank as of yet. 4A goes there. 2A, because there's no 3. And then 1A. Finally, bank 0A. Okay, bank 0 was the one we need to for sure modify. Okay. Let's reroute these wires. We don't want to do that quite yet. All these instructions need to be shifted over by 1 is what's happening here. Okay. And this goes there. We grab the LDI instruction. There we go. And then LDI gets deleted. And LDA gets moved over 1. And then LDA gets deleted. And gets replaced with the no-op. Okay, let's just rename this wire and then we're done. The reason we're adding a no-op instruction is because hopefully that'll result in us not having to do anything fancy to suppress action when the clock is in the down tick. We'll see. Okay. But currently we should be reading all zeros out of here, because the clock is in the down tick. We delete the Shin ISA. We need the Shin 16 ISA, which looks even more like a mutant than the Shin ISA did. Alright, it doesn't like that. It doesn't like that because PC is based directly on the output of, okay, yeah, we need to fix that. That is the last thing that's been done before the computer can actually start running, as PC needs to be determined properly. Wait, why is it complaining about address? Address should have nothing to do with that. Complaining that op select and address are tied together. Did I? Let's go look at this. I don't remember which one is actually the right output now. Oh, this is instruction. And this is result. I think I have them wired up backwards. Because we read the instruction first on the downtick, and then we read the result on the uptick if we need to read it. And yes, they are backwards. Oops. Okay. To result V. And it'll still complain about this. That's probably okay. But now at least it's complaining about the right line. Why is it still complaining about ADDR? ADDR has nothing to do with determining the output. Darn well better not have anything to do with determining that output anyway. That's what this multiplexer's for. Is it falsely determining that I might have to supply the clock signal externally? If that's the case. This giant field of offs over here is just to get the chip footprint square. And also so its name fits on its bulk. Now this should not be off. Because address... Now it's complaining about memory load. Memory load has nothing to do with reading PC. What are you on about? This line right here. That is the line that determines what address comes out on this. If I delete that, everything's fine according to this thing. Am I gonna have to do some kind of insane switch shenanigans to make this work? Nope, it doesn't like that either. Even if the switch is off, it doesn't like that. Weird. Okay. That's not correct, that's for sure. Okay, because what this is supposed to do is every other tick it does a thing. If I put a delay line in on address, don't use a multiplexer. Actually, wait, this might not even work. No, it should work. As long as PC is held high, it'll work. Yeah. As long as PC is held high, and address is energized on the same tick as the computer is on, this will work. Trying to think if I wanted to make these so that they had to come in at the same time, how would I... I'll just put a delay line on PC, but I can't do that because the whole point is that they need to come in at different times. The entire point of this is that we are toggling. Okay, here, let's move the clock outside. We're gonna have to put the clock external, I think. So this is the clock value off that leg. Somehow it's not complaining about those being tied together. So we need to provide a clock input now, not a clock output. Let's just put the clock input right where the clock output used to be. And we're going to have to do some reversing of... We have to do some reversing of NOT gates here. Okay. Now, when clock is high, we output. When clock is low, okay. When clock is low, we read the program counter and we put it into a delay line. When clock goes high, on the rising edge, you might say, we output, we read the memory if requested, and output it and the stored clock value. Then we read clock, we read the next program counter value. At this point, we read program counter. Boom, 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 boom. Okay. We now have external clock. Please work. There's no way. Where's it getting address from? Who's writing to address? Where does it think we're writing to address? What? This pin is low. This switch is off. It's tracing a line to circuitry that is currently off. That is not connected. This has got to be a bug. Because it is telling me that OpSelect is somehow some way feeding through this mess. I mean, I guess it's determining address by setting it to nothing. That's insane. Why would it pick this one instead of any other plausible path? Yeah, this is not a circular dependency. Because address is not currently being read. Address can't be read until this line goes high. Which I can confirm very easily because this is the address right here. No, this is the address right here. It's running into a multiplexer. And that multiplexer is not outputting address. It runs into a multiplexer and dead ends. Okay. Well, now what do I do? Because this has to work this way. Let's try switching schematic back to Shin. And then let's go to Shin 16. Nope. Yeah, it's not a circular dependency. Because this wire does not and cannot depend on the value of address. It very much does and can depend on the output of PC here, but not address. If we disable that, then it complains about it depending on memory load, which once again, it does not and cannot depend on memory load. If we disconnect everything except the ones that it actually does depend on, which it doesn't even depend on that one, then it's fine. That's bizarre. I'm willing to bet that if I copy the contents of this out, well, now that we no longer have much in here anymore, we could honestly just copy this out and try it. Okay. Delete all the unnecessary offs. And now let's compact this circuit. I'm willing to bet this will work outside of a, here I call it. Okay. Move that up a little bit. There we go. Grab this side's output circuitry. Squeeze it up against the edge. Grab the upper output circuitry. Move it down. Connect that up the way it goes. Oops. Move that in a good bit. Okay. Now, this is the load select, so we can move that up to the top here actually. Does not need to be down below the other one. Move that multiplexer down. Move that into place. Get rid of that. Reduce that. And there we go. We have a much more compact block. It's still kind of bulky, but more compact is definitely what I was going for. Go ahead and remove that block. Move the documentation block up to the top. Myself as much vertical space as I can. Clean up all the unnecessary pins. Okay, now this is memory V. This is program counter. This is ADDR. I think. Go ahead and collapse this a little bit more. Okay. Now, this is store. Yes. This is memory store. This is memory load. This is clock. Okay, now. We don't need clock over here anymore. Well, we do actually. We need to run these switches. And we need to run some more switches that come out of there, I think, eventually. Actually, no. Yeah. Okay. This switch... Oh, what did this switch do? It was part of the input enable for something, I think. I don't think it's important now. I'm probably wrong. Okay. Now. This is where PC is written in. This is the output from P. This is the PC output. Which means, in other words, the output of that delay line. And the output of this switch is result V. But not directly, because we only want result V to be turned on if we need an AND gate here. I think just a simple AND gate here is the right answer. We need to invert it again, of course. Otherwise the clock signal will be the wrong polarity. But basically, if the clock is currently high, and if the load is currently on, then we want to output to result V. The clock needs to go up one more line. Just one. Boom. Okay, and that'll allow us to move these lines up one, which will get us back into our allowed vertical area. Now, I think that's all. Everything's hooked up. As you see, there are no crossed wires. Nobody thinks that they are circuit dependency. There was entirely a bug with how it was handling custom circuits. Okay. Now, we need to have a bootloader. I'd like to do a hardware bootloader, because I don't have to try to write one. Because I need to be able to toggle, I need to be able to load the program from here into RAM, starting at a specified address. Which means I need a sort of pre-computer to run the computer. Until the program is written completely. Basically, we'll just read values from the program block. Actually, you know, I could just run the computer from the program block until a certain instruction is hit, and then toggle over to running from RAM. That way I could write a bootloader as program code. But then I would need to have a programmatic way to read from the program block. I don't think I'm going to do that. Instead, we're going to have a hardware loop that reads a 16-bit value from the program, writes it to RAM, increments the counter, increments a counter by 2, and repeats until the 16-bit value is 0. Let's do that. We'll start reading at block 0. We'll start reading from... Oh, actually, how do I want to do this? I need to pick a base address. I think I'm going to use 0 as the base address just because I'm lazy. We'll do a 16-bit. Do we have a 16-bit counter? Yes, we do. 16-bit counter. Okay. And then we do a 16-bit equality check. Put this... Oops. Not what I want to do at all. Oh, EP. Wrong button. Okay, there we go. Let's move the program block. The only reason I have the program block here at all is because it kind of made sense to put it there. Back when that was how you wrote your program. It's still how we write the program, but now I'm going to move it out so I can fit the bootloader between it and the rest of the block. Oops. Okay. Now, this counter is going to increment by 2. And it's going to output if and only if the counter is on, for which we need a latch of some sort. Okay, we're going to check to see if the output value is 0. This value gets fed back into the program address. Okay. If this value is 0, then we want to save that fact. As an on signal. I'd like to start this memory bit enabled. We can't, so we're going to have to invert it. Oh, we need to... There we go. Okay. Now we need a 6-bit switch. Two of them. We can use the same counter for address. As we do okay. All right. This counter's going to tick up forever, but we don't care, because as soon as we get a 0 out of here, we're going to shut it down. And then this needs to run over to memory store. And we need to put a diode on that. And additionally, we need a way to suppress the computer from starting until that shuts off. So what we're going to do is we're going to put a switch in here. this switch will turn on if and only if the system has finished booting. What's going to happen is this counter is going to tick until we get a 0 out of the program block. I need to also enable some other lines up here on the RAM to make it actually do its thing. Namely, we need to hold the clock high while this is happening. I think we can just do that with a diode. Here, let's put this NOT gate up here. Then we can just put a diode right there. Okay, what's it complaining about now? We need another diode, I think. There we go. Okay. Now, this delay line will do nothing because it won't never receive an on input until this turns on. But we'll hold the clock high. Which in this case is going to mean it's still booting. And a bunch of memory stuff will happen. Let's just step it, see if it works. Okay, what in the hell is it writing anyway? It's ignoring... Is this set to... No, it's set to 8-bit width. Oh, that's the problem. Yeah, it's ignoring the second byte. What in... Okay. It's ignoring the second line. Why does it have 4 save value lines when it can only use 1 at a time? He almost died. Jumped on a mushroom to get to the mushroom teleporter on Fossil Island, I'm guessing. I've never used the mushroom teleporters. How'd you almost die? I know there's some kind of mushroom-based fast travel on that island, but I've never used it. Took 42 of 43 health and damage. Okay, that sounds painful. Slightly. Why does it provide 4 inputs if you can only use 1? How in the hell do these RAM blocks even work? Like if I set it to 16-bit width, I bet you it'll work. No, it doesn't work even then. That's interesting. So those extra save values just do nothing? What happens if I run 16 bits into the first wire? Yeah, it takes only 8 bits of it. Okay. That's weird as hell. The outputs do work the way I think they do, don't they? Don't they? Why are there 4 values when only one can be used? You'd think it would work, like I was expecting it to work the same way the program block works, where it outputs first byte, second byte, third byte, and fourth byte when it's set to 8-bit width. But I'm just wondering if now they just have those on there for some vestigial reason and it doesn't actually work. Because if it doesn't work, that means it's going to take 4 ticks to do memory access. Or I'm going to have to do 16-bit width. And just give up byte addressable entirely. Unless I put a bunch of extra logic to extract low versus high byte depending on the address modulus 2. Even then that's not going to work because I'm going to have to read 2 bytes and then I might just have to give up byte addressable if this doesn't work. Which honestly isn't that big of a deal. It'd just be super annoying because I spent so much effort making dual addressable, byte addressable 16-bit RAM, only to have it not work. I'm going to do a quick search. Okay. Oh, I wonder if I know what those are for. What exactly are the whips provided? I bet you those only turn on when it's a 256-bit wide RAM. Why in the hell would you have 256-bit wide RAM? That's insane. Okay, whatever. That way you can load and store 4 64-bit values at a time. However, why would you ever want to be able to load 4 8-bit values at a time? That'd make sense. Developers. Okay. Alright, goodbye byte addressable, I guess. However, that does mean if we're not doing byte addressable, we can get rid of all the clock stuff and just use the dual load RAM, I think. Yeah, we can get rid of the clock. We could even load from the program memory faster. Matter of fact, I probably should. No, that'd be too hard to wire. Because they have to wire a special dual write mode. Which I don't think we can do even. Yeah, we can't write 2 at a time. We can only write... We can write 2 bytes at a time. We can't write... What do you call it? Yeah, the dual RAM only allows up to 64-bit. Okay, that would explain the insanity. However, just why? If I provide values on those pins, I want to be able to use them. Let me think about this for a second. Okay, well, you obviously need to go. We don't need a clock. We should rename clock to boot enable. So we can disable things while it's booting. Boot. Boot select. Okay, whatever. That'll work. What are you... Why does it insist on him drawing above my cursor like that? Whatever. It can be dealt with. This will make the computer a little bit more easy to use. Probably should use a pin on the flags for this instead, but oh well. That would mean really weird things would happen if you ever accidentally set the flags to the wrong value or something. Okay, now... Fast RAM. Goodbye. Dual RAM. Hello, welcome to the party. It does mean we don't need this weird delay line mess anymore. Okay. Load, save, address. That part all feeds in properly. We don't need a multiplexer here anymore for this. Okay. We have save value right below address, which conveniently enough is that line right there. Now we have load number 2, and we have address number 2. That is being provided by this. That is PC, otherwise known as program counter. Okay. Result V hooks to the top pin, and instruction hooks to the bottom pin, and it doesn't like something about that. Why not? I'll have to go figure this out in a second. It says address, watch, 16-bit width, it didn't like that size, I see. Really? Try removing. Oh, it's complaining about a lot more than the address. Load 2 isn't hooked to anything. Load to address is hooked to PC. Load 2 should be held high, actually. We should always be loading that. Why does it think that is a... Complains about address either way. Not that way, though. Why is it like this? We don't need these multiplexers anymore. They no longer have any meaning. Okay, this is memory load. This is memory store. That might have actually been part of the problem. Nope. What is its problem? This is about the simplest possible hookup. Okay, why are we running boot select through a diode, first of all? That's a relic of the past. Second of all, if boot select is on, we probably shouldn't be running address down into the rest of the computer. Matter of fact, the whole bus should be shut off if boot select is off. Trying to lay out an entire bus shut off is reasonable right now. It's going to show me some weird disconnected. Yeah. Even if I was to disconnect this, it would just transfer the problem somewhere else. It's going to say literally anything that could ever write to address is determining the result, which is nonsensical, because address has nothing to do with the output on this wire, or at least it isn't supposed to. It's supposed to be this address line. Now disconnect address and it immediately moves to load. Yeah. That's demented. Okay. If I were to put a multiplexer in there and use a separate address line for the bootloader, it would still complain. I'm willing to bet. Okay, no one else is energizing the address line, right? Let's try attaching a 16-bit constant. To the address line. And let's see if it blows up. Yeah, nobody else is energizing the address line. The only thing that's energizing the address line is this switch right here, which is how it's supposed to be. It's just being really weird about the output of the RAM. The dual RAM is apparently not implemented properly. It thinks that it is, what an annoying bug. It doesn't help that it doesn't want to let me set a size in bytes when the data width is 16 either. Okay, what do you want from me? Alright, I think I screwed up big time. We need to go back to the old system. But I can't because I need the dual load RAM. But I can actually, I think. Yeah, I can. If I use the old clock system, I'm gonna have to do stuff. Let's see. I'm really shocked that 1024 isn't valid. Oh wait, does it just reset the size back to 0 without... It does. It is working, because it changes the gate score over here. It just resets these to 0 after it's done, because that makes sense. Yeah, this is a particularly intractable bug. And I think I'm going to have to go back to the worst system. Basically, I'm going to get the worst of both worlds because this is bugged. We have to do 2-cycle memory access when there's a solution to do 1-cycle memory access. Unless there's some way make it recognize that the top 4 pins have nothing to do with this. Like this, that's sort of kind of valid. But the other way is not. That is not an okay thing here. Let me see if I can figure out anything about this. Trying to Google the dual load RAM for this game does not give me anything useful. Oh. Okay. Well, that's not very helpful. Let's see if I can cause this issue to happen. Just do this, we have access to an 8-bit wire. Okay. Oh, fine, be that way. Hello? Oh. Yeah. Okay. There's only one way that this could possibly be viewed as a circular dependency, and that is if you were trying to save to the address at the same time. But there should be a tick of delay. Anyway, we're not going to be able to use the dual load RAM. So, why did I delete all that? Because we're just going to have to control Z it all. Hopefully the on-delete buffer is, or the undo buffer is deep enough for this. Because I don't want to have to rebuild all that stuff. The dual RAM. And I accidentally went a little too far and removed some of the infrastructure related to the bootloader. And there's no redo, there's just undo. Oh, that's annoying. But not ultimately a big deal. Okay, this needs to be set to 16-bit data width. Boom. See, this one doesn't zero it out when you set the values. It remembers them. Like a proper program should. Okay. Back that to the input. Now, we need to do some suppression here on the clock. Then we need a couple diodes. Hold the clock high while we're bootloading. And this should step through memory. Until we get a 0, at which point I'll stop. We have all these stupid multiplexers and stuff around because it has to do every other. Alright, let's try. I have to go fix it so it no longer steps by 2 anymore. Boom. Program counter still does not tick up, by the way. I probably should make program counter a 16-bit counter now. Yeah, that'd be a valid thing to do. Okay. And we want that to count by ones because we're not doing byte addressable memory anymore. Alas, RAM is buggy. Oh, I mean to lock the program counter. When the bootloader's done. You know what? I regret everything I just did there. Okay. We will implement an adder for the program counter. Oh, we're gonna have to write the program counter from something else. I can either try to do some kind of system that resets the program counter to 0. In either case, if the program counter is running, I need something to suppress it. I need a way to suppress the program counter and stop it from counting, which means we can't use this as a counter. It has to be a register. It could be a delay line. If we did the same thing as flags and make it a delay line, we wouldn't be able to do it that way though. We'd have to do some more complicated logic than that. We need a multiplexer. A 16-bit multiplexer. Okay. So far, so good. And then this line would run to the output from the clock tick. You know what? Okay, so this case, we need to set up a system that every other tick let's do the clock circuitry right in here. Okay, which one of you writes to okay, so it's the bottom wire that writes when the clock is high. So the bottom wire is the one we want to feed into the program counter current value, I think. The top wire gets program counter. Okay, this gets program counter and this gets program counter +1. Not that simple though, because if it was that simple, I would just do a 16-bit adder and feed the clock into the carry. And there was some reason I didn't do that, and I can't remember what it was, damn it. So I thought of that. And then I thought, no, I can't do it because of X. And I can't remember what X is now. But you know, I think I actually can do that. And I'm going to assume that I was right, and I can actually do it. Until and unless... Let me delete it, damn you. There we go. Something proves otherwise. Okay. So the clock is high. Oh, we need to invert that. If the clock is low, program counter is just going to be set equal to program counter. If the clock is high, the program counter will be set to program counter plus 1. And I should move this logic be up here somewhere. That was a terrible idea. I do want to move that logic though, because I'd rather be above the system up there. So we have to go down and around because of logistical issues, but okay. That's the program counter set line. And this gets connected to the clock, which is the only thing in the computer so far that's been connected to the clock that isn't outside of the memory load area. So this is basically the same as this, but with the option to increment or not, depending on the clock. So this will cause the clock to tick ahead every other simulation tick. Which should be correct. Okay. Now, since we hold the clock high while we are doing... We are holding the clock high, right? Yes, we are. Okay. Okay, so the bootloader part is at least partially working. Go ahead and delete that entire program. Let's enter a much shorter program. LDI 5 STA. Wait. STA. IO. Okay. This should load immediate 5 and then store it to the IO. Boom. Very simple. Okay. It's not incrementing properly here. This does need to increment by 2 still. $16.5. It does not need to increment by 2. I mean, it does, but it doesn't. The easiest way to do this, I think, is going to shift the value. Left 1 bit. That is not how that's supposed to be hooked up, but it should work. Okay, 15.5, 32.9, 0. Pop. We're over to normal operation now. Okay, the clock is currently high. Now the clock is low. No, the clock is high still. There we go. Now we load the first instruction. The problem is, yeah, okay, we load the first instruction. It goes into delay line. Boom. We write the first instruction. And unfortunately, I think I see a problem. Because we should not be outputting there just yet. Yes. Okay, let's try that again. Boom. Boom. First 16 bytes written. Boom. Extra cycle. Pop. It ticks over. I think I need a delay line. Somewhere. Okay, tick. Now with the next tick, we should load the first instruction. Boom. First instruction is loaded. Okay. With the next tick, that switch should shut off. Okay. I see a bit of a problem. The program counter is advancing every single tick. And the clock remains stuck in the off position. Why does the clock remain stuck in the off position? Probably because I forgot to put a NOT gate up here. And how did this ever work in the first place? Because this switch was never doing its job. Okay, the clock was pre-primed. It should not have been. Boom, load, load, boom. Tick over, clock priming. Should begin next tick. Clock is primed. Boom. Clock is high. Boom. Clock is low. Boom. Clock is high. Yeah, the problem is, due to the nature of the system, the clock has to be high. For this to work? Okay. Something is wrong here. Okay, well, the bootloader part is working. Up to the point where the clock kicks on. At that point, it seems like clock being high. Okay, when the clock is high, the computer should work, actually. That is how that's supposed to work. That is incorrect for how this is working, though. But the reason the clock is being held high is because we want to write to the RAM. So until the first low signal from the clock, the computer shouldn't start. And the problem is... Okay, so this... We want to add 1 to the program counter during the down cycle. I don't know if that's a good idea or if that's going to cause bugs. But we're adding 1 to the same cycle that we're using the program counter. I think that's going to cause bugs. Because we want to either add one or store the program counter, not both. So this would technically be correct. However, this is going to mean that the clock is going to tick while the bootloader is enabled. So we need to disable clock to the rest of the system. Like, memory still needs to receive clock, but the rest of the system cannot receive clock until the bootloader ticks off. Okay. We actually want to connect this to the actual bootloader output. So until the bootloader kicks off, the rest of the system does not receive clock. Only the RAM receives clock. A little bit janky. Should work. And we don't want the clock to tick until then either. Okay. Now, any other interesting bugs that might exist? While the clock is high, okay, we can only write to the delay line when clock is low. Means the next tick let's just test it, see what happens. We load the first one, we load the second one. Boom. Clock ticks over. Okay, next cycle. We have a dead cycle here, basically. Boom. Computer resets. Clock starts ticking. Clock goes low for the upper part of the system for the first time, basically. We are currently reading our first instruction. Clock goes high. We write our first instruction out. The RAM is now in read state. If it, it could. RAM is enabled to talk to the RAM bus in this state if it wanted to, which it doesn't. And we are adding one to the program counter. Okay. At this point, we are doing LDI. Okay. This is going to be hard as hell to debug. Because after we load the program into RAM, we don't have any control over the program anymore. We can single step it and try to guess what's going on, but we don't know where it's at. We can't use any debugging stuff. Kind of a nightmare. We'd have to do some really advanced address bullshit to try to split the RAM and program into separate memory regions that are still accessible using the same API. Just one section is ROM. But I can still execute code outside of the ROM, and yeah, no thanks. Because if we can't execute code, we can't have an interactive system without having, I mean, we could, but we can't do an interactive system the way I want to do an interactive system without being able to access our own code. Well, No, we need to be able to jump into RAM to execute. We could have some code be in ROM. Like we could have a region of memory be in ROM. But we can't have all of it be in ROM. And I'm tempted to tear out some of these changes and make it so that addresses above a certain amount are ROM. Pick some large address and have like the top 2K bytes or something be ROM. Specifically the program block ROM. Then we would just have the computer start at boot loading from that address. Finally finishing the Holy Grail quest. I don't remember that one at all. Been far too long. I really wish you could go back and replay quests, because some of those quests are kind of cool and I'd like to replay them. 10 prayer levels is nothing to sneeze at, that's for sure. Prayer is such a pain to raise. One of the reasons why I want to get a house built, because I want to... yeah, you know what? I think we're going to do that. Because just thinking about the debugging problems of not being able to have access to this stuff, for starters. Loading the program into RAM is a cool idea. I'm glad I got it to work. We are executing that program. We got the values coming out here. We are indeed loading a 5. We are not indeed loading a 5. Why not? Oh, because LDI is incorrectly encoded. Yeah, I forgot to change the... LDI is actually LDA. Oops. So we are doing 0, 1, 2, 3, 4, 5. Yep, this one right here. We're loading this register instead of the constant 5. And then the call to STA is actually going to do LDI, which is completely wrong. All right. Let's fix that, why don't we? Let's just go ahead and add the NOP instruction. Then we need to do LDA, which is now instruction 1. LDI. Now instruction 2. STA. It's now instruction 3. And SCF. There we go. Now it should work. Boom. First computer tick right there. Also, we'll skip the whole bootloader sequence if we do mapping the program into memory at some point. Let's see. Maximum 16-bit value. I don't want that. I want 16-bit constant. Boom. Maximum 16-bit value is Lord, like 64,000 something or other. 65,000, whatever. Okay, whatever. If we do... The bottom half of the address range is RAM, the top half as ROM. That'll make it really easy. And we'll only care. We'll have plenty of RAM space. Actually, here, wait, I don't want to do that. Okay, I can't enter -1 in there. Boom. Let's just go ahead and... Boom. Let's max out our RAM block. We do enter the value in bytes and not the units of width, so that's fine. That should give us more than enough RAM for anything I ever want to do, and then a bunch more besides. And program doesn't appear to be limited in size. So now what we want to do is only on low ticks. We want to check address and decide between the program block or the RAM block. We could delete all the bootloader stuff. Which is honestly a bit of a relief. Bootloader was cool. Don't get me wrong. But it was also a little bit janky. Okay. I'm going to leave the program block where it's at, because I like its location. But we're going to have to insert some extra logic around it to make it work. Okay, that is PC. Yes. We'll run PC into here. However, we're going to have a switch. We need a 16-bit splitter. And then we need a 16-bit maker. And we need to run output 2 directly to byte 2. No. Output 1 directly to byte 1. Output 2 has to go through a byte splitter maker pair. Because we want to cut off the high byte. The high bit, whatever. 8, 16, 32, 64. Boom. Okay, I screwed that up very slightly. Yes, okay. Byte 1 goes straight through. And then we get a 16-bit switch. Boom. Actually, no, wait. We don't care what it's outputting when we're not using the value. There. Okay. So this will be instruction value. Oh, we also only want to use this when clock is high. But actually, that'll run right into there, I think. We need an AND gate here. That's clock. Yes, okay. So when clock is high and we are requesting that the program value come from ROM, then we feed that into the ISA. Otherwise, we need this same exact bit of fun and excitement here, over here. Except over here, we'll use it with inverted meaning. Okay. So this will be used for address. We don't want it over here. We need it over here. Let's move this down a little bit to get out of the way. Okay. This will be used for address if and only if another 16-bit switch. Don't like where that's placed at all. I don't like having anything across from these, except possibly wires are running past. Let's move this block down one space. That'll give me room to want to run a wire through. Okay. Boom. Okay, this one needs to be inverted. Boom. Okay. So we're asking for a value lower than, without its top bit set. Additionally, is there a way to set the delay line ahead of time? No, there is not. Okay. That's unfortunate, because I really need to set that delay line high to start. I can't load a value into RAM to start either, so we're going to have some kind of boot procedure that will cause a jump instruction to be the very first thing to be executed. All right. go ahead and encode instruction. Oh, that's a problem actually. All the jump instructions are 8-bit offsets. They need to be 16-bit offsets. And we can't do that because we can't provide 16-bit constants. Well, offsets will work. But like the jump instruction itself needs to be re-encoded to be a take it from a register. I can't really do that. I'm gonna need to add a lot more instructions to do some of this stuff. We need instructions to set the high bit, instructions to set the low bit. Or low byte, I mean. Low and high byte. Like LDI, we need to load immediate as high, load immediate as low. We can't just have LDI. Load immediate as low would be the normal thing to do if you're trying to load a small value. If you're trying to load a large value, you're going to have a multi-step process. Yay. Reconnection. Reconnection. Alright. Well, at least it wasn't down for long. Oh. All you've heard for the last 2 hours is I beat the game, so I'm gonna make it harder and redo half it all over. You're not wrong, Survey. You are not wrong. I don't know about harder, though. Well, kind of, I guess. I'm preparing to do something much more complicated than they are asking you to do, so yes, that would be harder, I guess. Because for those who weren't here last night to hear me talk about what I was planning to do with this computer, I am preparing to make this computer capable of implementing Forth on it. I want to write a Forth for it. And to do that, I need to have the ability to run the program out of RAM, or the ability to execute RAM. Because otherwise you wouldn't be able to implement any, you wouldn't be able to define words. And I need the ability to reference memory more easily. That's basically why we're going to 16-bit. Because I want to have the whole address fit into a register. Because otherwise it's going to become too hard to deal with. I could do it using, I could have done it with the old system, just using the 8-bit addresses and the bank registers. But I would be constantly having to keep track of what bank I'm in, when I need to switch bank. Yeah, it would not have ended well, let's put it that way. I would have quickly driven myself nuts trying to get the memory system to work properly. So we're basically making memory easier to handle, because we're going to have to do a lot of memory access for writing Forth. What problem was I trying to solve before I got distracted? Next project, replicate this whole thing in Minecraft? No. Building circuits in Minecraft just isn't fun. Not for me anyway. Like building a small circuit to do some concrete mechanical thing, that's great. Building a large complicated circuit to try to build a computer in Minecraft just to run calculations, no. Not fun. You spend too much time trying to figure out how to make gates and not enough time trying to figure out how to make the gates work together. It's kind of cool as a you can do it kind of way, but it's not cool in a actually doing the mechanics of making it. You get really tired of Minecraft's building system if you even build a simple computer. Because I have messed around with building computers in Minecraft before. Just like a simple ALU and stuff like that, but... trying to do even a 4-bit adder. That way lieth insanity very quickly. Of course, that was before slime blocks were even a thing, and so it'd be a little easier now than it would be back then. But even so. I was doing something and realized I had some kind of problem. I don't remember what it was. Oh yes, I need to jump into the right address somehow. I could invert this logic and make it ROM be the first X number. Oh, and the other thing was that I can't even encode a jump instruction. Okay. I might hardcode address 0. To be a jump instruction. No, that's dumb. I just need to figure out a way to set an initial value for PC. And it's not going to let me set this delay line. If I could give this delay line an initial value, we would solve all our problems. Well, not all of our problems, but the most important part of our problems. The next most important part of our problems is how I'm going to encode jump instructions and things like that. I almost need to do variable instruction sizes. Which if I did that, I could do it. I would have to encode the size of the instruction into the ISA. Which means I need to adjust every single instruction in the entire ISA. All 100 and some odd of them. You know, that's including the dummy instructions. And then I would have to add another line to the bus. Well, I wouldn't technically need that line because it only needs to go one place. Although technically most of these lines in the bus aren't important anyway because they don't go anywhere either. They go to the registers. And like a few things use select values. So I guess it is important to have those on the bus. But like size of instruction isn't necessarily needed. But for that I'd also need byte addressable, which I don't have byte addressable. So I can't do variable size instructions unless I code the jump instruction somehow so it... No, that's dumb. No, I wouldn't be able to do that. So I'm not going to be able to use labels. Unless... I either write my own assembler and just have it output bytes that I paste into the program block, which is going to make debugging a bit hell. Well, I wouldn't need to have it complete. It wouldn't have to be completely that way. Debugging's gonna be a bit hell anyway, because it's gonna sometimes run the program and sometimes not. Because it will jump out of the program block and run stuff in RAM sometimes. You can't just sit there and step through in the program block. You'll eventually hit code that will jump to RAM and execute before returning to the program block, which might make this very confused. It might make the poor thing not know how to do its... I want to have bytes, the low bytes, be RAM, because that'll be easier. I'm more likely to want to hardcode addresses in RAM and not in the ROM. But labels are going to be completely out the window. And jump instructions are going to have a range of 256 bytes, which is unacceptable as they're currently encoded. Like, if you look at the jump instructions, all of the jump instructions, all of them take a hard-coded address, an immediate address, which made sense at the time. It did limit our size of our programs, but it wasn't a problem because none of our programs are anywhere close to that large. So we have to change all of these to take, which means that isn't hard to do in the ISA, but it does mean we can't use labels at all, which we keep getting back to that problem. And if we do use labels, their values are all going to be wrong. Because their values are all going to be 8-bit. We need them to be 16-bit. Unless I have an instruction specifically for generating an address, which I guess I don't really need one of those. I can just I could do a thing where I keep track of the base address of a function, and then I jump to offsets and stuff, but I really think we're just not going to be able to use labels, which is going to be a huge problem because every time you edit the code, it's going to throw everything off. I'm basically going to have to write an assembler that handles that stage for me. Because if I change the data width to 16, that is totally a thing I could do. However, that makes each little thing I type in here be 16 whole bits wide, which is not viable. Because the whole instruction is supposed to be 16 bits wide. Yeah, we got a bit of a problem here, I think. I wonder if I should hard code the null instruction as a jump. To a known destination. Where the known destination... Actually, you know what? That is a brilliant idea. That would be a way to get bootstrapping working. Change the name of NOP to boot. And just hard code. Let's see, where even is it? Defined. It's block 0, so it's up here at the top. Right there. Hard code this instruction to be jump to beginning of code segment. I could totally do it too. Yeah, let's go do that. That's gonna save me so much trouble. Okay. Block 0. We still haven't fixed all of our problems, or even most of our problems. But this is fixing an important boot. Okay. The boot instruction wants to write its result to PC, which is register 4. Boom. And it takes no arguments. Okay. Now, all we need to do is when boot is on, we just take and write a 16-bit constant to the output. Which, conveniently enough, is right there. All right. And the constant in question is, boom, address 0 of the high range. In other words, please jump to the first byte of the program memory. Okay. And it will keep doing that forever and ever and ever because there's no instructions in the program memory. Okay. That's a lovely idea, actually. I'm glad I just thought of that. That saves me a lot of effort. Okay, but that does not solve the jumps problem. All of those need to be re-encoded. Point to registers. Because there's no way to provide a 16-bit constant as it stands. Which means we can't even load a 16-bit constant into a register until we provide a way to do that. Which means it is time for the text editor of doom. All right. Planning. Okay. Bank no longer needs to exist. Boom. It's still there. It's still called bank. There is a register there. I mean, it's still called bank in the assembler, but there's a register there. It just doesn't have a name anymore. Matter of fact, I'm going to take this opportunity to go into the program real quick here, and we're going to delete the name for bank. Boom. All right. We no longer have a register named bank. Give me that back at text editor. Register 7 is unused. At some point, I'll think of something that I really need a register for, and we'll put it on register 7. Flags are unchanged. I went through a good bit of effort to make sure flags could be completely unchanged. This needs to be changed to be boot. Jump to the first byte of the ROM region. Okay. Now, LDI. This needs to be changed. We need LDI. We're going to have LDI, load immediate. And we're going to have LD high. Load parameter as immediate value into I byte of A. Why'd I have a T there? I don't know. Don't ask me. Okay. This will allow us to, in 2 steps, load a constant that is 16-bit. Kind of wasteful, but loading constants hopefully isn't something we have to do very often. I think group 3, I'm going to use this group to do instructions for reading keyboard input, because we have to do that yet. We have to read keyboard input. There's no point in making a 4th if it's not interactive. We have to read keyboard input and probably files. We'll start with just keyboard input though. Yeah. I should get rid of IO as a register. And put IO instructions in here in group 3. I'll think about it. Oh, for now we're not gonna put anything in there. So we have LDI and LD high. The address stuff is fine. You know, the memory access stuff. Because these are just offsets. These are intended to be used for things like reading arrays and stuff. Having those be 8-bit values is acceptable in my mind. If you need to have a larger offset than that, then you're doing something wrong. Or you're just going to have to handle it yourself. I'm sorry. I I might regret this later, but we're just going to leave that alone. I highly doubt I will, because 256 16-bit values, that's a lot of memory. Because that's what your range is with those offsets. If you really need to, you can always add something to I or K and do it from there. Same way with the stack pointers. Store A to D stack indirect frame, parameter is immediate offset. That's fine. LDF, same deal. Load A from D stack indirect frame. Offset. If your frame is more than 256 16-bit values, then you need to rethink your life choices, please. We don't need these instructions for setting the memory banks anymore because they don't do anything. Let's go make the changes I made so far. Let's add LD high. And let's remove the, what are they called again? SDMB and SRMB. Okay. First of all, let's hide line. Go in here. SRMB, goodbye. SDMB, goodbye. Those are in group 2. Need to go modify the ISA. Group 2. Boom. Boom. Turn these both back into null instructions. Okay. We have more space now in group 1. That might be useful. Not group 2, I mean. I don't think I needed anything in group 2. I was pretty happy with that one. Okay. Now we need to go to group 0. And we need to move STA and SCF. Up 1 each. Okay. Oh, oops. Gotta grab the label too. Okay. Wait, why did I do that? Okay, and then you and you get changed. Be there. Okay. And this becomes LD high, which is such a silly pun. We should have LD low instead of LDI, but I can't help it. It's a silly pun. And I like it. Okay, so SCF, STA need to have their encodings changed. Okay. STA. SCF. Okay. Where's LDI? LD high. Now, we need to go... Okay, those two were disabled already. Of course, when I tore out the extra logic over here. We need to go find group 0. Group 0 has no special logic for anything, pretty much. Which is actually bad in this case. Because we're going to have to insert some special logic. So we have LDA, LDI, LD high. SCF. I don't just run these straight across. The original reason why they weren't running straight across is because, I don't know, I wasn't thinking. It made sense at the time. Okay, so this will work for LDI, but not for LD high. Also, we don't need the collapse instruction there anymore. So what we need to do is the input needs to be shifted 8 bits. There's arithmetic shift right. We don't care about that right now, though. We need shift left. And then this needs to be set to the 8-bit constant. 7. Actually, no. I think it does actually have to be set to 8. Yeah, because shifting 0 means do nothing. Okay. This should allow us to load a proper 8-bit value. Except, this isn't quite right even yet. Because we need to then OR 2 values together. Get the actual final value. So we need to wire R2 into this somehow. Well, it's a good thing we got a little bit more space below this. We can maintain our spacing rules. Boom. I should collapse most of these together a little bit. Oh well, we'll deal with it later. Or we probably won't. Okay, so we need to go set R2V to be register A. No, not you. The ISA. Okay. Need to modify load high, which is in group 0. And I do believe the game just crashed. Okay. Well. First time for everything, I guess. At least it loads quickly. Okay, which computer are we looking at here? This is definitely the Shin 16. Okay. We want LD high. So you need to be set to 0 for A register. Okay. That should work. This is such a stupid hack. But anyway. Now, I do believe that we should probably test that. So, let's do LDI. Zero. Let's do okay. And then so this will execute a boot instruction. The first tick will. And now we should be executing LDI. Or we will be executing LDI. Oh yes, every other tick. That's right. That's right. Got a lot of phantom information wandering around though. That's a problem. Okay. We need to turn off output from this. Okay. Let's modify the ISA. We need to add another pin. We'll just put it up here because it doesn't matter. We've long given up on trying to have nice looking stuff. And then we will redo all of these with switched outputs. I think this will be the right solution. The idea being that we feed clock into this, or rather inverted clock. I should probably invert this internally. Oops. Okay. 1 bit, NOT gate. Boom. Okay. We'll call that clock. There's no point in naming any of these pins because they're all too small to read. Okay. This is wrong. Okay, first of all, just move that down. Second of all, we only want to output when the clock is high. I forgot. Clock high mean computer running, not computer currently loading instruction. Okay. This means the select lines are all low. There's no giant fuss going on. This is currently outputting a weird value for PC. Should I only have this on when clock is on? Because this is currently the only thing that will actually enable itself when the rest of the bus is off. I think I need to do that. Wait, I need a 16-bit. Yeah, 16-bit switch. I'm just going to stick it out here because that'll be way easier to enable. Boom. Okay. Oh, and I forgot to hook this up as well. And that needs to be, of course, needs to be switched. Yes, I know how frickin' short circuit works. Actually, this switch can go away. Okay, there we go. Now, forgot to move the switch and I put the OR gate in. I just put it on top instead of where it actually had to go. This should stop the computer from getting weird between cycles. I hope. Boom. First take. Okay. Lock is enabled. We're executing the boot instruction. Boom, we're loading the next instruction. PC is set to a really high value. Boom. We're executing load high, or load. We're executing LDI. Or we should be anyway. So this is passing through the value. The constant thing is enabled here. 222. Yeah, that's what I have encoded here. If I change it to this, it makes much more sense. We're loading DE. And then we do next tick. And we get a short circuit. Okay, why do we get a short circuit? Because you and you are both outputting to argument 2. Why are both of you outputting to argument 2? Oh. Okay, I see what the problem is. These need to be before the switches. Duh. And these need to be 16-bit switches. Okay. That's honestly blindingly obvious. Why did I do it that way in the first place? I don't know. Why do I do anything? $16-bit switches. Oops. Okay. Goes down a little bit. And then we need 16-bit makers. I almost did the same thing again. You would think I would know better by now. Okay. This should actually just work like this without the 16-bit makers. Because the 8-bit value should... There's a lot of shoulds in there. But it should just write the low 8 bits of the 16-bit value. Let's go ahead and try it. Boom. Boom. Okay, there we go. Yup, it's working. Boom. Boom. We hit the halt. Okay. What exactly is going wrong here? Boom. Boom. Okay, what are we executing right now? Clock is on. Looks like we're executing the boot instruction. Yeah. Clock off. Load. Oh, you know what? No, this is fine. Okay, there we go. Okay. This is supposed to be storing DE in the low bytes, which it's doing. Clock off. Oh, this needs to be... Okay. Come to a halt. So this needs to have its addresses shifted by 1 bit. Specifically, it needs... I'm gonna have to implement my own shift because I don't think shift comes with a carry. I'm gonna have to do shift with carry if I use a 8-bit shift, which is what I need here. But that's not hard. We can just implement our own shift, no problem. Problem is, we don't really have the space for this. That needs to be moved down. This needs to be moved up. Make room. Actually, this does not need to be moved up. Boom. But this does need to be moved down even more. Okay. And the whole mess needs to be moved out. Space. Okay. Oops. The good news is this gives us an insane amount of ROM. Okay. Is this actually going to work, though, is the question. Yes, it will. At least at first. Okay, it will work. And that should be the halt instruction. Okay, it says hit halt. And unfortunately that appears to have erased our value in the register. Either erase the value in the register or worse, that value got erased ahead of time. Oh. That's a problem. That's a pretty big problem, actually. When the clock is off, it's overwriting register 0. I think we actually need to shift all the registers one that way and remove the old bank register completely. Or rather, we need to remove the A register and then re-encode all the instructions. That A is register 1 and register 0 points nowhere. That, or we could suppress output from this decoder. That's pretty far easier. Based on the value of clock. There we go. We suppress output based on the value of clock. We don't care about the load select. I don't think. Okay, there we go. ADDE, the expected result. Although if you wrote it out low to high, it would be DEAD. But that's not how you write things out, so that's exactly what I would expect. Okay. And then if we execute one more step, or two more steps, we get hit halt instruction. Okay, so this computer is starting to very slowly become operable. It's still a bit janky here and there. Jump instructions are nonsensical. I mean, I guess you could use none of them. Okay, let's go fix group 4B. That's not how you go fix group 4B. This is how you go fix group 4B. Okay. Every single one of these needs to not be immediate. Why are the first two blank? This is JNC and JC. Jump if carry, jump if not carry. Jump if 0, jump if not 0. Jump if negative, jump if not negative. Jump if overflow, jump if not no overflow. Okay. Unfortunately, this makes the computer a little less usable. Because now to get labels to work, what would I actually have to do to get a label to work? I mean, labels will still function for the first 256 bytes of program code, but only if we do a real bit of song and dance here. You just do LD high. Let's do this. How did I mangle that so much? Label X. Okay. We want this to halt with 0 instead of halt with 1. So we want to jump to X. We'll jump to A instead. We need to LD high X, or LDI X. And then we need to do, oh shit, we can't even do that. Yeah, okay, we do. Then we need to do STA R0. Okay, we've got X into a register. And then we need to do LDI. Let's do it in binary. And then we do LD high. Actually, let me think. No, we want these to all be zeros. Okay. So this should have the A register now having just the high bit set. And then we need to do OR R0. So we set the high bit of the X register using this abomination. In reality, we would probably do a function. Now you might see where problems begin. We can't call functions by name. We can't do label thing pop R PC like we normally would, and then do call thing, because these are RAM addresses. We need to turn them into ROM addresses. We need to set their high bit. And the only way to set their high bit, or not the only way, but the easy way, is just to OR them. And then, not to mention, they have to be into a register to get called to even work with them. Speaking of which, call needs to be fixed. That is in group 4A. As is jump. Okay. Oh. it makes no sense for call and jump to be loading from a register. However, what I really need to do is make call be a 2 instruction operation. So call, and then a 16-byte address as the next instruction. So call needs to increment PC by 2 and somehow read the next address as well, which we are not set up to do at all. Jump needs to do the same. All the other jump instructions need to do the same. Unless we have a complete second set of jump instructions to jump to things in ROM versus jump to things in RAM, and that is completely unacceptable. And even then, it's still going to limit us to the first so many instructions. The first 256 of them, which is extra unacceptable. So how do we do multi-field instructions on this machine? First of all, let's see if this even works. Short circuits. When ORing. How even? You're trying to write to result V. That switch is trying to... Oh. Okay, that's the wrong solution to that problem. No wonder it didn't work. Even this isn't really the right solution to this problem, I don't think. Think about this for a minute. Okay, so we need clock to be high and this to be on before this switch activates. Where can I run the clock wire? You can run it across the top. Okay, what's your problem? Output leads to its own input. What fun. Oh, why are we using flags used and not clock? Oops. Okay, there we go. Now, where's the halt? There we go. If it works, we should see it say halt 1. It's obviously not working. Okay, why is halt not being triggered? because the A register apparently does not hold the right value. Boom. Okay. Why does A hold 0? We need to step once more. Okay, there we go. Okay. And I should be writing this result to the A register, which it is. And then we do pick. And then next tick, the jump should execute. Boom. Okay. Why? Is it saying 04 for result select? Because that's the PC. Okay, that's where it should be saying. Oh, I never did fix jump. That's why. Yeah, it's saying arg2 const 0. Okay, I forgot to fix those instructions in 4A. I fixed 4B, but not 4A. Okay. All right, let's run it. Well, it halted, but it didn't tell me what I wanted to see. No, it didn't halt. Okay. So we should be energizing the jump circuitry. We are not energizing the jump circuitry. Wait, is clock high? No, clock is low. Oops. Okay, now clock is high. Okay, we are energizing the jump circuitry. We are copying through 80 E, and we are attempting to write that to the program counter. Okay. I think the problem is the delay line. Doesn't make any sense though. No, because next ticket should be outputting ADE. Which should be $14, alt 0. Instead, it's outputting all zeros. Where did it jump to? It jumped way farther out than it was supposed to. Yeah, because it jumped out here to this 0 instruction. Which is completely wrong. It should be like here. Yeah, E is supposed to be 14. It should have jumped to here. Instead of wherever in the hell we are. Oh. That doesn't make any sense though. Yeah, it does make sense. Makes perfect sense. It's the shifting that did it. Oops. Here. It's the shifting that did it. We need to jump. This is an even bigger problem. Because ROM addresses we need to divide the address by 2 then. After we OR the address, we need to then shift the address right 1 space. No. We need to do shift it right 1 space before we OR it. Yeah. We need to load the address. We need to shift it right 1 space. We need to load a mask. We need to OR it with the mask. Because otherwise, if we do the ORing first, then that screws it up and we jump into RAM instead. And it still didn't work. Hello? Okay, what address are we getting? Okay. Now we have a slightly different problem. Because we need to account for the fact that it is going to multiply our address by 1. Or by 2, I mean. And shifting it yeah, this isn't working. Because ROM addresses, we're trying to build a ROM address from a simple number. We shouldn't need to shift it, though. Matter of fact, the shifting just made it worse. But that is why we got to where we got to. Because this value... The shifting shouldn't have made it worse, though. Let's run that again. Okay. This is telling it to go to ROM address 0C. Or go to ROM address 12, which is halt 1. If I step it again, now it's telling it to go to ROM address 16 instead. I think we actually fixed the problem with this shift, except we're getting a spurious addition on this jump. It is incrementing it when it shouldn't be. But that doesn't even make sense, even so. Because after the shift, it then says to go to 32, which is completely off in the boonies. Okay, so this resets the program because we hit our boot instruction. Wham! It jumps off into the boonies and goes back to a reboot. That's not what's supposed to happen. Boom. Execute boot. Execute LDI. Execute shift right. Execute STA. Execute LDI. Execute LD high. Do the OR. Okay. What is the value being stored in A right now? 32784. Which is 8010. Which is wrong. Like X should be 14. Where's that calculator? I want to check something real quick. Okay, we want... Go ahead and type in 14 and then set the high bit. And that should give me 80E. Okay, except we don't actually want 14, we want 7. On second thought. And with the high bit set, that's 8007. Okay, well, we're getting 8006 instead. Right this instant. We check, it's saying 8010, which is definitely not correct. Why is... Oh. Yes. No, we're trying to... No, that's right. We're trying to jump to 16. I keep thinking of this. No, the label is for the... Label's for 16. Derp. The 10 is correct. Except it isn't. It's supposed to be half of that. So something is going weird with the shift. Let's start over from the top. Okay. Boom. We've jumped into ROM now. Go find the shift area. Clock is low. Boom. Okay, we are executing the shift right now. No, we're executing the load right now. Derp. Okay, now we're executing the shift. Shift right. It's saying we're shifting it by 0. Oh, it's not shift immediate, it's shift in register. Derp. Okay. LDI 1 STI STA R1 shift right by R1. Okay. Now we're executing LDI. Store 1 to R1. Store X. Shift left by 1. Shift right by 1, I mean. I would be kind of surprised if this one didn't work now. Yep. Hit halt instruction with a 0. Which is exactly what we should. Okay, so this is the simple code that we need to get a simple jump to label to work. As you may imagine, this amount of screwing about to turn a label into a proper address is completely unacceptable. We could add an instruction to do all this quite easily, because most of this could be removed. Like, this is just loading these two are just loading the constant 1 into a register so that we can use it for a shift. We can easily hard code a shift right by 1 somewhere. This is just loading immediate. We can do that easily enough. This is doing the shift, which that's just a simple gate. Or, you know, it's not a single gate, but it's a simple chip. This is loading a mask, which you can just set a bit. That's much easier. So really all we're doing is shifting, setting a bit, and then doing the normal jump stuff. We could easily code that all into the jump instruction to do all of this. However, that would mean that instruction can only work with ROM. It would kind of make sense to do this for the call instruction, but not for any of the jump instructions, because those we might want to jump to RAM. And as a matter of fact, it doesn't even make sense for the call instruction, because what if we want to call a function that's stored in RAM? No, you can't do that. We could have a separate instruction that took a label and turned it into an address and stored it in a register. But that's going to be more complicated as well, because once again, we don't really want to be... I guess we could take the old bank register and turn it into an address register that is used for the jump instructions. And then just give jump a dummy. Jump would have an offset, so we would say jump 0 would be jump to the address in the ADDR register, or ADR register, or whatever. And then we would have a couple different load address instructions. That's probably what we're going to end up having to do. And this mess to take a label and turn it into a valid ROM address is not acceptable either. That needs to be modified. The problem is, I'm not sure what's going to happen. Let's make a new program. Okay. There's 8 bytes. Let's push this out far enough and then let's see how it encodes the label. Okay. I don't think this is quite far enough, but okay, that's definitely far enough. That's past the 8-bit limit. Let's actually remove test from here. We can put it up at the beginning. All right. What is the value in RAM at the beginning? Or ROM, I should say. 5100. Okay. Why do I keep hitting the wrong? There we go. That is not 337. If we do 337 minus 255, we get... Yep, okay. So, it discards the high bits, is what it does. So what the label really should be doing is doing... Why in the hell? There. This is what I would really like to put there. But it doesn't, because, and that makes sense why it doesn't. But this is its actual value. So for long programs, labels are completely out. And that is where you would want labels, so I'm not sure what I'm going to do here. This is really not written for long programs, I guess. At least not with the current. Yeah, so I would like to delete that program. Okay. I'm basically going to have to write my own assembler if I want to get anything good out of this. Because most of our problems revolving around the program block are revolving around the program block and the way it encodes instructions. We might just have to go back to using a bootloader to load stuff into RAM. And have the program block not even exist. Use a file loader instead to load the initial boot ROM, so to speak. Or we can just load the program as binary, as pre-encoded binary. That means for next week, I might need to get streaming from Linux set up. If I want to write an assembler. Or I could just write the assembler on my own time and present it next week. Not like it'll be hard. I've done very similar things before. Matter of fact, it'd be downright trivial. It is going to require more faffing about. And generally a slightly less usable interface. We won't be able to have a working debugger. Not really. I mean, I guess. I still need to figure out the jump problem and the call problem, because having the current solution of having them stored in registers is just not a good idea. I need some way to do 16-bit immediate operands. Which means we really need to provide a way of doing 2-cell instructions. Which means certain instructions are going to have to pause the clock, do a second read, and somehow stuff that second instruction byte or second instruction word onto a thing somewhere. I don't know, I'll think about it. Or I won't. But it's kind of an intractable problem at the moment with this design. But currently we have a 16-bit computer that works but not well enough to actually use for anything. And that'll have to do for now, because it is 10:53 and it is time to go to bed. Oh, who am I kidding? I'm not going to bed yet. But I'm going to end stream. And we'll see. I'll probably continue this next week. Probably with some slightly different tooling and maybe a slightly better plan. Or knowing me, without any plan whatsoever and without any tooling. But we'll see. It looks like Avi and Wasted are playing Red Dead Redemption. Okay. Let's raid Avi. Sure, why not? Tomorrow, I will be engaged in some sort of activity. I have no idea what yet. Guess we'll see when we get there. Maybe if a crab beta comes out, we'll play a little crab or something. And of course, Tuesday, there will be more Dungeon Siege 2, and we'll continue the rest of the week from there. And hopefully more Turing Complete next weekend. But anyway, until then, I hope you'll have an awesome night over at Avi's, and I will see you all later. Good night, and goodbye.